This table feels solid, doesn't it? You can knock on it. Rest your coffee on it. Your own hands, the chair you're sitting on, the ground beneath your feet, our entire world seems built on the fundamental certainty of solidness. It's the first rule of reality we learn as kids. You can't walk through walls. But what if everything you think is solid, isn't? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. What if I told you that this feeling of solidity is just a clever illusion? A trick our senses play on us? That if you could shrink down, smaller and smaller, past the finest speck of dust, you would find that the world you know is a lie. What if we took a journey to the very edge of physical reality, a place where the concept of a thing, a solid, dependable object, dissolves into a ghost world of pure potential? Well, that's exactly the journey we're taking today. We are going to peel back the layers of the world you think you know, descending through the scales of existence until we arrive at the startling, beautiful, and profoundly strange foundation of reality itself. A place where structure, as we understand it, breaks. The world we think we know, matter and solidity. Before we get too weird, let's ground ourselves right here, in the world we can see and touch. What do we actually mean when we say something is matter? It sounds simple, but it's the bedrock of this whole investigation. Picture yourself picking up a stone. It has properties you can instantly recognize. It has weight. You feel the pull of gravity on it, a heft in your palm. That quality, that resistance to being moved, is what physicists call asterisk mass. It also takes up space. It has asterisk volume. It displaces the air around it, and if you try to put your finger where the stone is, it pushes back. It asserts its own presence. So, in the language of classical physics, matter is simply anything that has mass and takes up space. Seems intuitive, right? Almost too simple. And we see this principle everywhere, in the different states of matter we run into every day. Think of an ice cube. It's a solid. Its particles are locked into a rigid structure, giving it a definite shape and volume. You can't just pour it like water. Melt that ice cube, and you get a liquid. The particles are now free to slide past one another. The water flows to take the shape of its container, but it still has a definite volume. If you spill half a cup, the other half doesn't just expand to fill the void. It remains, stubbornly occupying its own space. Now, boil that water. It turns into steam, a gas. Here, the particles go wild, zipping around and expanding to fill whatever container they're in. But even a gas is matter. You can prove it with a simple balloon. An empty balloon on a scale has a certain weight. Fill it with air, and it gets heavier. That invisible stuff inside has mass and takes up space. You can feel it push back when you squeeze the balloon. This is the world our senses perceive. A world of solids, liquids, and gases. A world of tangible stuff. This rock is hard. This water is wet. This air is, well, it's there. This is our starting point. The familiar, comfortable reality we all agree on. But this is also where the illusion begins. Because the very reason you can feel that rock in your hand, the reason it feels solid and impenetrable, has almost nothing to do with it being truly full of substance. The wild truth, the first hint of the strangeness to come, is that the sensation of touch is a lie. The first step down, the molecular city. Let's take our first step down. Our first stop on this journey inward is the molecular level. Imagine that the wooden table from our intro isn't one solid thing, but a sprawling, impossibly dense city. The buildings of this city are the molecules. For wood, these are gigantic, complex structures, long chains of cellulose and lignin all bound together. In the water we imagined, the molecules are much simpler. Little bundles of two hydrogen atoms clinging to one oxygen atom, hydrogen oxide. In the air, it's mostly molecules of two nitrogen atoms, N2, and two oxygen atoms, O2. At this scale, the neat divisions between solid, liquid, and gas become less about the stuff itself and more about energy and connection. In a solid, our molecular buildings are packed together in a rigid, crystalline lattice or a dense grid. They're connected by powerful electromagnetic bonds, like a web of invisible springs. The molecules aren't sitting still. They're constantly vibrating, humming with thermal energy. But they're held firmly in place, unable to break away from their neighbors. This is what gives a solid its structure. In a liquid, the molecules have more energy. They vibrate more intensely, enough to overcome the rigid bonds that held them in place. They can now slip and slide past one another, like people in a dense crowd. The connections are still there. Surface tension is a perfect example of molecules clinging to each other. But they're fleeting, constantly breaking and reforming. This is why a liquid can flow. In a gas, the molecules have so much energy that they've broken free from each other almost completely. They fly around at incredible speeds, bouncing off each other and the walls of their container in a chaotic, high-energy dance. The city is no longer a packed grid. It's a vast, empty space where buildings occasionally smash into each other. Even at this first level, our idea of solid is already starting to shift. A solid object isn't one continuous thing. It's a huge collection of individual parts, a commonwealth of molecules held together by invisible forces. The difference between a hard rock and the air you breathe isn't as absolute as it seems. It's just a difference in energy and freedom. But these molecules, these buildings in our microscopic city, aren't the end of the story. They aren't fundamental. They are, themselves, built from even smaller, even more mysterious components. To continue our journey, we have to pick one of these buildings and zoom in further. We need to see what it's made of. And this is where the world we know truly begins to dissolve. We're leaving the familiar realm of chemistry and entering the unnerving emptiness of the atom. The atomic void, mostly empty space. If molecules are the buildings of our city, then atoms are the bricks, the steel, the glass, the fundamental units everything is built from. Everything you've ever touched, tasted, or seen is made of atoms. And yet, the reality of an atom is one of the most mind-bending concepts in all of science. Let's zoom in on a single water molecule. We see our one oxygen atom and its two smaller hydrogen companions. Let's just focus on the oxygen. From a distance, it looks like a tiny, solid sphere. But as we get closer, that illusion of solidity just vanishes. We find ourselves in a region of shocking emptiness. In the far, far distance, we can just make out a tiny, impossibly dense point of light. This is the atomic nucleus. Circulating in the vast, dark void around it are indistinct, cloud-like presences. These are the electrons. The scale here is staggering, and it completely demolishes our everyday perception of matter. If we were to scale up an atom so that its nucleus, just protons and neutrons, was the size of a marble on the 50-yard line of a football stadium, the electrons would be like a few specks of dust swirling around the nosebleed seats. Everything in between, the entire volume of that stadium, would be, for all intents and purposes, completely empty space. Your body is made of trillions upon trillions of these atoms. The chair you're in, the air you're breathing, they're all built from these mostly empty spheres. This means that you, and everything around you, are made of 99.9999999% empty space. This is a profound and deeply weird revelation. It leads to an immediate, burning question. If the table is mostly empty space, and my hand is mostly empty space, then why can't I just push my hand right through it? Why does it feel solid at all? The answer is our first real taste of the ghost world we're looking for. The solidity you feel is not from two objects making physical contact. It's the result of invisible forces. The electron clouds around the atoms in your hand and the atoms in the table are both negatively charged. And as you might remember from playing with magnets, like charges repel. As your hand gets close to the table, the electron clouds of its atoms get close to the electron clouds of the table's atoms. An invisible but powerful field of electromagnetic repulsion flares up between them. That force is so strong it stops the atoms from ever actually touching or passing through one another. So, when you touch a table, you are not physically touching it. Your hand never makes contact. What you're feeling is the electromagnetic force of the table's atoms pushing back against the atoms of your hand. Solidity is a force field. It's an illusion created by charge and repulsion. But there's an even deeper rule at play here, one that forms the very basis of structure itself. It's called the Pauli exclusion principle. This fundamental quantum rule says that no two identical particles called fermions, which includes electrons, can occupy the same quantum state. Think of it as a cosmic law of personal space. Each electron in an atom needs its own unique address, defined by its energy and spin. When you push on the table, you're trying to force the electrons in your hand into the same quantum states already occupied by the table's electrons. The Pauli exclusion principle forbids this. Making that happen would require a colossal amount of energy. This resistance to compression is what gives matter its bulk and form. Without the Pauli exclusion principle, all atoms would collapse, and the universe as we know it, with its rich chemistry, its structure, couldn't exist. Matter would just collapse into a super-dense, featureless soup. So, our idea of a solid object has now been demolished twice. First, it's not continuous, but made of molecules. Then, the atoms making up those molecules are almost entirely empty space. And now, we see that the feeling of solidity is a ghost story told by invisible forces and a bizarre quantum rule about personal space. We've reached the edge of the classical world. To go deeper, we have to journey into the nucleus at the heart of the atom, and from there, into the true heart of the mystery, the quantum realm. The heart of the matter, the subatomic zoo. Having pierced the atom's illusion of solidity and floated through its vast emptiness, our journey now takes us to that tiny, dense point at its center, the nucleus. Here, in a space so dense that a teaspoon of it would weigh billions of tons, we find a new cast of characters. These are the protons and neutrons. For a long time, we thought these were the end of the line, the final, indivisible bits of matter. But as we got better at smashing them together in giant particle accelerators, we found out that they, too, are composite objects. Like Russian nesting dolls of reality, there's another layer inside. If you could crack open a proton or a neutron, you'd find an even more bizarre world, populated by truly fundamental particles called asterisk quarks. Specifically, each proton and neutron is made of 3 quarks, swimming in a frantic soup of energy and other particles. This is where we meet the asterisk standard model of particle physics asterisk, humanity's best and most successful theory for describing the fundamental pieces of the universe. The standard model is like a family tree for all the particles we know. It tells us that everything in the universe is made from just 12 fundamental matter particles, interacting through 4 fundamental forces. The matter particles come in 2 families, quarks and asterisk leptons. There are 6 types of quarks, with whimsical names like up, down, charm, strange, top, and bottom. Up and down quarks are the most common. 2 up quarks and 1 down quark make a proton, while 1 up quark and 2 down quarks make a neutron. All the heavier quarks are unstable and quickly decay into their lighter cousins. The other family, the leptons, includes the electron we've already met. Like quarks, electrons have heavier, unstable siblings called the muon and the tau. Also in this family are 3 ghostly particles called neutrinos, which are so light and interact so rarely that trillions of them are streaming through your body every second without you ever noticing. So that's it. The recipe for all the matter you've ever known, from stars to starfish to your own heart, is surprisingly simple. A handful of up quarks, down quarks, and electrons. Every other particle is just a more exotic, short-lived version of that. But what holds them together? Why does the nucleus, packed with positively charged protons that should be repelling each other like crazy, not fly apart instantly? The answer is the other half of the Standard Model. The asterisk force carrying particles asterisk, known as asterisk bosons. In the quantum world, forces aren't just invisible fields. They are carried by the constant exchange of these particles. The electromagnetic force, which keeps electrons orbiting the nucleus and stops your hand from passing through the table, is carried by the asterisk photon. That's the particle of light. When two electrons repel each other, they are actually tossing photons back and forth. Inside the nucleus, the incredible repulsion between protons is crushed by an even more powerful force, the asterisk strong nuclear force. This force is carried by particles called asterisk gluons asterisk, and it acts like an unbreakable cosmic glue, binding quarks together. The strong force is astonishingly powerful, but its range is incredibly short, confined to the nucleus itself. The third force is the asterisk weak nuclear force. Carried by W and Z bosons, this force is responsible for radioactive decay. It's what allows a neutron to change into a proton, a process essential for the nuclear reactions that power our sun. Of course, there's a fourth fundamental force we all experience, gravity. It's the most obvious force in our big world, but it is mysteriously missing from the Standard Model. At the particle scale, gravity is so mind-bogglingly weak it's almost completely negligible. Unifying quantum theory with Einstein's theory of gravity remains the single greatest challenge in modern physics. So now we have our cast: quarks, leptons, and bosons. The Lego bricks of reality and the forces that stick them together. We seem to have found a solid foundation. These particles, we're told, are point particles. They have no physical size. They are the end of the line. But what are they? Tiny, spinning balls? And how do we explain the bizarre fact that an electron, a particle, can somehow also act like a wave? To answer that, we have to take one last step. A step into a place where the very idea of a particle finally breaks down. The turning point, when classical physics fails. For centuries, the world of physics was neatly divided. You had particles, tiny, discrete objects like billiard balls. They had a definite position. And you had waves, spread out disturbances, like ripples on a pond. An object was either a particle or a wave. It couldn't be both. This classical view worked perfectly for everything we could see. But in the early 20th century, as scientists probed the atomic realm, they found a paradox that would shatter this division and introduce the strange new rules of quantum mechanics. The story starts with a deceptively simple experiment, one that has been called the most beautiful and baffling in all of physics: the asterisk double-slit experiment. Here's the setup. Imagine a barrier with two thin, parallel slits in it. You fire tiny pellets, like marbles, at it. On the other side is a screen that records where they land. What do you expect to see? Two distinct bands, one behind each slit. This is how particles behave. Now, instead of pellets, let's use water waves. As the waves pass through the two slits, they spread out and interfere with each other. Where two crests meet, you get a bigger wave. Where a crest meets a trough, they cancel out. The result on the screen isn't two bands. It's a pattern of many bright and dark stripes, called an asterisk interference pattern. This is the undeniable signature of a wave. Now for the moment that broke physics. Scientists did this experiment with electrons, which they thought were just unimaginably tiny pellets. They fired them one at a time, so there was no way they could bounce off each other. If you close one slit, you get what you expect: a single band of dots behind the open slit. Close the other, you get a band behind that one. Just like the marbles. But when you open both slits and fire the electrons one by one, something impossible happens. The first electron makes a single dot. The second, a single dot somewhere else. The third, another dot. At first, it looks random. But as thousands upon thousands of electrons hit the screen, an astonishing picture emerges. It's not two bands. It's an interference pattern. Let that sink in. The electrons, fired one at a time and detected as single particles, are somehow behaving like waves. This pattern can only form if each individual electron, traveling alone, somehow goes through both slits at the same time, interferes with itself, and then lands at a single point determined by that interference. This is asterisk wave-particle duality. At the fundamental level, everything, electrons, photons, even atoms, exhibits this schizophrenic nature. They are neither classical particles nor classical waves. They're quantum objects. The moment you try to find out which slit the electron went through, say, by placing a detector at one slit, the interference pattern vanishes. The very act of observing its path forces the electron to choose a slit, and it goes back to behaving like a simple particle. It's as if the universe refuses to show you its wave-like and particle-like nature at the same time. This isn't just a quirk. It's a fundamental law. It tells us that, at the quantum level, particles don't have definite properties like position until they're measured. Before that, they exist in a state of pure potential. The wave that creates the pattern isn't a wave of matter, but a asterisk wave of probability. It describes all the possible places the electron could be. This discovery was the turning point. It signaled the death of the old, deterministic, clockwork universe. In the quantum world, you can't predict anything with certainty. You can only calculate probabilities. The universe, at its most fundamental level, isn't a clockwork machine, it's a game of chance. And this leads to our final destination. If an electron isn't really a particle or a wave, but a cloud of probability, what is it a probability of? We're now ready to descend into the place where structure truly breaks, the world of quantum fields. The climax, where structure breaks, fields, waves, and probability. We've arrived at the bottom floor of reality, as far as modern physics can take us. Here, in the realm of quantum field theory, the very concepts of particle and empty space lose their meaning and merge into something far more fundamental. The ultimate answer to the question, what is an electron, is not a tiny ball of charge. The answer is, an electron is a localized, vibrating excitation of the electron field. Let that idea settle in. The universe, at its most basic level, isn't made of tiny particles moving through space. Instead, the universe is made of invisible, all-pervading fields. There's an electron field that permeates all of spacetime. There's an up quark field, a down quark field, a photon field, a field for every fundamental particle. These fields are everywhere. They are the fundamental substance of reality. Most of the time, they're quiet, lying in their lowest energy state. In this state, we perceive nothing. We call it a vacuum or empty space. But empty space isn't empty. It's a simmering cauldron of potential. If you pump enough energy into a specific point in one of these fields, say, by smashing two particles together at nearly the speed of light, you can cause the field to ripple, to vibrate. That localized vibration is what we perceive and measure as a asterisk particle. An electron is not a asterisk thing. It's a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. All the particles in the universe are just the music of these fundamental fields. This perspective beautifully resolves the wave-particle duality paradox. A particle is a wave in its underlying field. When we observe it, we interact with a localized packet of that wave's energy, so we detect it as a single point-like particle. The fields obey wave-like rules of probability, while their interactions are discrete and particle-like. So, where does structure break? It breaks right here. At this level, there are no solid objects. There are no tiny billiard balls. There is no stuff in the way we understand it. There is only the ceaseless, energetic hum of invisible fields. The universe is a vast orchestra of these vibrating fields, and the particles we see are just the individual notes. And it gets stranger. This empty space isn't actually quiet. Because of quantum uncertainty, for incredibly brief moments, the fields can borrow energy from the vacuum, allowing pairs of particles and their antimatter counterparts to spontaneously pop into existence, only to annihilate each other and vanish an instant later. These fleeting apparitions are called virtual particles. Space-time, at the smallest possible scales, isn't smooth and calm. It's a chaotic, bubbling, seething frenzy of these virtual particles constantly appearing and disappearing. The physicist John Wheeler gave this concept a beautifully evocative name, quantum foam. From a distance, space-time looks like a smooth ocean. But as you zoom into this unimaginable scale, you find a violent, frothing turmoil. This is the true nature of the vacuum, a dynamic, shimmering sea of pure potential, where the boundary between existence and non-existence is constantly blurred. This is the ultimate destination of our journey. We started with a solid table. We journeyed down through molecules, atoms, and subatomic particles, watching our concept of solidity dissolve at every step. And now we have arrived at the foundation. A universe not of things, but of fields. A reality where particles are mere ripples on a universal ocean, and empty space itself is a foaming, bubbling soup of fleeting ghosts. The idea of structure has completely broken down, replaced by a world of pure mathematics, energy, and probability. The new reality, implications of the ghost world. We've journeyed to the bedrock of the physical world and found that it's not made of rock at all. It's a world of shimmering fields, probability waves, and foaming quantum energy. The solid, predictable reality we live in is an emergent property, a large-scale illusion born from the unbelievably strange rules of the very small. Standing here, at the end of our descent, we have to face the mind-bending implications of this new reality. The world isn't just stranger than we imagine, it might be stranger than we can imagine. One of the most profound consequences is the death of simple determinism. The classical idea of a clockwork universe, where the future is perfectly predictable, is gone. At its core, the universe is fundamentally probabilistic. You can never know with certainty what a particle will do next, you can only calculate the odds. This has led to a century-long debate. Was Einstein wrong when he famously declared, "God does not play dice"? Most interpretations of quantum mechanics today suggest that the probability isn't a measure of our ignorance, but a fundamental feature of reality itself. The universe genuinely does play dice. Then there's the concept of quantum entanglement. This is a phenomenon, which Einstein called spooky action at a distance, where two or more particles become linked so their fates are intertwined, no matter how far apart they are. If you have two entangled electrons, and you measure one to have its spin up, you know the other will instantly be found to have its spin down. In the language of fields, this isn't so spooky. The two particles aren't separate things sending faster than light signals. They are part of a single, unified excitation within the field. They're two aspects of one indivisible quantum state spread across space. Measuring one part of the state instantly tells you about the other, because they were never truly separate to begin with. This deep interconnectedness suggests that at the fundamental level, the universe isn't a collection of individual parts, but a single, indivisible whole. Perhaps the most significant implication is how this journey reframes our own existence. We look at our hands, the same hands we started with, which still feel so solid and real. And we now understand what they truly are. They are a temporary, complex, and astonishingly beautiful pattern of excitations in the fundamental fields of the universe. A stable, self-perpetuating storm of quantum ripples, held together for a brief moment in time by the fundamental forces of nature. The atoms that make you up were forged in the hearts of stars billions of years ago. The quarks, the leptons, the fields themselves, they're as old as the universe. You aren't separate from the cosmos, you're a thinking, feeling, wondering piece of it. A way for the universe to look back on itself and marvel at its own strangeness. This ghost world of probability and force isn't something distant. It is you. It is the table. It's the light entering your eyes right now. The illusion of the solid, classical world isn't a lie that hides the truth, but a magnificent story that the truth tells about itself on a grander scale. Conclusion. The wonder of it all. We began our journey by touching a wooden table. We asked a simple question. Why does it feel solid? That question led us down a path that dismantled our reality, step by step. We journeyed through the bustling city of molecules, then into the vast, lonely void of the atom, where solidity was revealed to be an illusion of force and quantum exclusion. We dove into the nucleus, discovering the frantic zoo of quarks and gluons. We saw classical physics fail in the face of wave-particle duality, forcing us to accept a world governed not by certainty but by probability. And finally, we arrived at the foundation. A universe made not of things, but of fields. Where particles are just notes in a cosmic symphony, and empty space is a seething foam of virtual ghosts. We have reached the place where structure, as we know it, breaks. So, what do we do with this knowledge? How do we live in a world that we know is, fundamentally, an illusion? We do it by embracing the wonder. The fact that the universe isn't what it seems is not a cause for despair, but for profound awe. It means reality is richer, deeper, and more mysterious than we ever could have guessed. The strange rules of quantum mechanics are the very rules that make life and complexity possible. The Pauli exclusion principle, which felt so abstract, is the reason atoms have structure, why chemistry works, why stars don't collapse, and why you are a solid being who can sit and ponder these questions. Let's zoom back out now, ascending through the layers. We see the fields coalesce into particles. The particles form atoms. The atoms bond into molecules. The molecules build the intricate structures of wood, water, and air. The ghost world of probability solidifies, and the illusion of the macroscopic world reasserts itself. You can knock on the table again. It still feels solid, but now, you know the secret. You know that the feeling in your knuckles is a conversation between the quantum fields that make up your hand and the quantum fields that make up the table. You know that what you perceive as a solid, stable object is, in fact, a magnificent, complex, and deeply elegant dance of force and probability, playing out across the fabric of space-time. The world is not less real because its foundation is strange, it is infinitely more marvelous. And the journey to understand it, the journey to where structure breaks, is the greatest adventure there is. If this journey into the heart of reality blew your mind, make sure to subscribe and hit that notification bell. We dive into the biggest questions in the universe every week. And let me know in the comments. What concept in physics do you find the most baffling and incredible? You have never actually touched anything. Go on, do it. Press your hand down on the table. Clap your hands. Feel that? That feeling of solid on solid. The firm resistance of the table, the sharp smack of your palms hitting. It feels like one of the most basic truths of our existence. The world is solid. It has substance. It pushes back. But what if I told you that feeling is a trick? A beautiful, elaborate trick played on you by the fundamental forces of the universe. What if I told you that your hand didn't actually touch that table? That your palms never, ever made contact? In fact, what if I told you that you have never, not once in your entire life, truly touched anything at all? Right now, as you sit there, you are levitating. You're hovering a microscopic, almost impossibly small distance above your chair, held up by an invisible force field. The same goes for the floor under your feet and the phone in your hand. There is always a gap. An uncrossable, untouchable void. This probably sounds like late-night philosophy, not a description of reality. But the science on this is crystal clear. The matter that makes you, me, and everything we think of as solid is made of atoms. And atoms are famous for being almost entirely empty space. If the nucleus of an atom were the size of a pea sitting on the 50-yard line of a football stadium, its electrons would be like specks of dust swirling around in the nosebleed seats. Everything else? Nothing. Emptiness. So here's the big question. How can a world made of 99.999% nothing feel so solid? If your body and the wall in front of you are both just ghostly collections of nearly empty atoms, why can't you just walk right through it? The answer isn't in what's there, but in the forces holding it all together. It's a story that takes us from the world we think we know down to the bizarre, fuzzy reality of quantum mechanics. It's the story of the invisible rule that stops our universe from collapsing into a dense soup, and in doing so, creates our entire experience of a tangible, touchable world. So, stick with me, because we're about to pull back the curtain on reality itself. You might just find the universe is a whole lot weirder and more elegant than you ever thought. Deconstructing the atom, the great emptiness. To get our heads around this grand illusion of touch, we have to first take apart what we think we know about matter. We need to shrink ourselves down, way smaller than any microscope can see, and journey into the heart of a single atom. Most of us have a mental picture of an atom from school, the Bohr model. It's a neat little solar system with a dense nucleus like the Sun, and tiny planet-like electrons zipping around in clean orbits. It's a tidy image, and it's a useful starting point. But, as we'll see, it's also completely wrong. Still, let's use this little solar system model for a second, just to get a feel for the ridiculous scales we're talking about. Imagine we take one atom from the tip of your finger and blow it up to a massive size. Let's make its nucleus, that ball of protons and neutrons, the size of a single green pea. Now, let's put that pea on the 50-yard line of a giant football stadium. So, where are the electrons? The other stuff that makes up the atom. You might picture them as tiny pinheads orbiting close by. But they'd be smaller than a grain of sand. And they wouldn't be anywhere near the field. The innermost electrons would be orbiting somewhere out past the cheap seats. The outermost electrons, the ones responsible for basically all of chemistry and, as we'll find out, the sensation of touch, would be circling way out by the stadium's outer walls, maybe even in the parking lot. Everything in between, the entire vast, cavernous space from the grass on the field to the highest seat, is, in this picture, totally empty. That's the atom. One tiny nucleus, a few even tinier electrons miles away, and a whole lot of nothing. The real number is even more mind-boggling. An atom is about 99.9999999999996% empty space. Now, let's apply this. Your hand is a collection of trillions of these empty atoms. The table is also a collection of trillions of empty atoms. When you bring these two collections of atomic solar systems together, why don't they just pass right through each other? Like two clouds of dust? With all that emptiness, it seems like the tiny nucleus of one atom could easily slip through the vast void of another. Your brain is probably screaming that this is impossible. You can't just phase through a wall. The evidence of your entire life is overwhelming. Things are solid, and that contradiction is the key. The fact that the world feels solid, even though it's made of what's essentially structured emptiness, tells us something else must be going on. There has to be an invisible force, a rulebook for the universe, that stops these atomic ghosts from passing through each other. The solidity we feel isn't matter bumping into other matter. It's the feeling of being powerfully repelled by an invisible force field. You're not making contact, you're being pushed away. And the force responsible for this universal repulsion is one of the four fundamental forces of nature: electromagnetism. The invisible wall, electrostatic repulsion. Our universe runs on four fundamental forces: gravity, the strong and weak nuclear forces, and electromagnetism. Gravity holds the planets and keeps you on the ground. The nuclear forces hold the atom's nucleus together. But the force that governs almost every single interaction in your daily life, from friction to chemistry to the light you're seeing with right now, is electromagnetism. And at the core of electromagnetism is a simple rule you learned with bar magnets: opposites attract, and likes repel. Two north poles will push each other away with a real, tangible force. At the atomic level, we're dealing with positive and negative electric charges. The nucleus has positively charged protons. Orbiting the nucleus are negatively charged electrons. And it's these electrons, especially the ones in the outermost shells, that are the gatekeepers for every single object in the universe. When you move your hand toward a table, what's really happening is that the atoms in your skin are getting close to the atoms in the wood. Long before the nucleus of an atom in your hand could ever get near a nucleus in the table, the outermost electrons of those atoms start to feel each other. Think of those two bars magnets again. When they're far apart, nothing. But as you bring their north poles closer, you start to feel a resistance. An invisible cushion of force builds up. The closer you push, the harder it pushes back. You can strain and struggle, but you'll never actually get those two faces to physically touch. The magnetic field between them becomes too powerful. That is almost exactly what happens with your atoms. As the electron shells of your hand's atoms get incredibly close to the electron shells of the table's atoms, we're talking distances of a few angstroms, a massive repulsive force just appears. This is called electrostatic repulsion. It's the law that particles with the same charge, like the negative electrons in your hand and the negative electrons in the table, powerfully push each other apart. The closer they get, the stronger this force becomes. It skyrockets, creating an invisible, impenetrable wall of pure force. The atoms in your finger are literally stopped dead in their tracks by the electrons of the table. So, what's that sensation you call touch? When you press down, what are your nerves actually sensing? They're not detecting contact. They're detecting the force of that repulsion. Your nerves are just incredibly sensitive pressure detectors. As you push, the electron clouds in your fingertips get squeezed against the electron clouds of the table. This huge repulsive force pushes back on your skin, squishing the cells. Your nerve endings register this pressure, send a signal to your brain, and your brain interprets this storm of atomic repulsion as the simple feeling of touch. You are feeling a force field. Every time you lean against a wall, the solidness you feel is just the collective rage of trillions of electron shells refusing to share their space. The floor holding you up right now is generating an electromagnetic force that perfectly cancels out the force of gravity pulling you down. You are, in a very real way, floating on a sea of electrons. This is why things have shape and structure. It's why we can build bridges that don't fall down. The entire idea of solidity is a large-scale illusion, born from the microscopic refusal of electrons to get too close. But this still leaves a piece of the puzzle unsolved. The picture of atoms as tiny solar systems, while useful, isn't the whole story. To really get it, we have to embrace the beautiful weirdness of quantum mechanics. Correcting the picture, the fuzzy electron cloud. That idea of an atom as a mini solar system, the Bohr model, was revolutionary for its time. But as physics dug deeper, the picture started to break down. The reality, as described by quantum mechanics, is far stranger and, frankly, cooler. Electrons are not tiny, hard little balls orbiting a nucleus. One of the core ideas of quantum mechanics, the Heisenberg uncertainty principle, says you can't know both the exact position and the exact momentum of an electron at the same time. The better you know where it is, the less you know where it's going, and vice versa. And this isn't because our tools aren't good enough, it's a fundamental property of reality. Because of this, an electron doesn't exist at one single point in its orbit. It exists as a wave function, a cloud of probability. The best way to picture it isn't as a planet on a track, but as a literal cloud. This cloud represents all the possible places the electron could be. It's denser where the probability of finding the electron is high, and thinner where it's low. But the key is this: the electron isn't moving through the cloud. In a very real sense, the electron is the cloud. It is smeared out, existing in all these places at once until it interacts with something. Think of a single blade on a fan. When it's off, you see the blade and the empty space. But turn it on, and the blade spins so fast it blurs into a transparent disk. You can't point to the blade anymore. It effectively occupies that whole circle. You can't stick your finger through the empty space because you'll hit a blade. The electron cloud is like that, but in 3D and governed by probability instead of speed. A single electron in its orbital doesn't leave the rest of the atom empty. It fills that entire volume with its presence, its probability, and its charge. So that idea of the atom being mostly empty space is itself a bit of a misnomer. The mass is tiny and concentrated, but the atom's volume is fully occupied by these fuzzy, probabilistic electron clouds. And this quantum picture makes the illusion of touch make even more sense. When your hand approaches a table, it's not tiny points interacting. It's these huge, diffuse, negatively charged electron clouds that start to overlap. Imagine trying to push two of those spinning fans together. The blades would start clattering into each other long before the centers could ever touch. It's the same idea here. As the electron cloud of your atoms begins to mix with the electron cloud of the table's atoms, the odds of two negative electrons finding themselves in the same spot goes way up. And that's when the electrostatic repulsion we talked about kicks in with a vengeance. It's the repulsion between these fuzzy, ghost-like probability clouds that creates the force we feel as solidness. You're not pushing solid against solid. You are squishing probability fields against other probability fields. The world feels solid not because it's full of stuff, but because it's full of fields that refuse to share their space. The role of stability and other forces. Okay, but wait a second. If the main story here is repulsion, with every atom pushing every other atom away, why doesn't everything just fly apart? What holds anything together in the first place? The answer is a beautiful cosmic balancing act. The same electromagnetic force causing repulsion is also responsible for attraction. While all those negatively charged electrons are pushing each other away, they are also powerfully attracted to the positively charged protons in the nucleus of their own atom. There's a repulsive force trying to expand the atom, and an attractive force pulling it all back in. The stable size of an atom is the perfect equilibrium point where all those forces are in balance. But there's another, even deeper quantum rule that's essential for the stability of matter. This is the famous Pauli exclusion principle. Simply put, the Pauli exclusion principle is the universe's ultimate, personal space rule for particles like electrons. It states that no two identical electrons can be in the exact same quantum state, in the same place, at the same time. A quantum state is like an electron's unique address, its energy, its spin, its orbital shape. Each electron in an atom must have its own unique address. They can't all just pile into the best spot closest to the nucleus. This is why atoms have their shell structure and why chemistry works at all. But how does this stop you from falling through the floor? While electrostatic repulsion is the force you actually feel, the Pauli exclusion principle is the rigid law that prevents a total collapse. As you press on a table, you're trying to force the electron clouds to overlap. If you could somehow push hard enough to overcome the raw force of repulsion, the Pauli exclusion principle would be the next line of defense. It would forbid the electrons from your hand from moving into the already filled quantum states of the table's electrons. Forcing them any closer would require an insane amount of energy, the kind you find inside a star. This creates a kind of pressure that makes matter incredibly stiff and resistant to being compressed. So you have two things happening. Electrostatic repulsion is the force that says, "Hey, get out of my bubble," while the Pauli exclusion principle is the fundamental law that says, "And besides, there's literally no room for you in here anyway." Together, they create the stable, solid world we know. The philosophical implications and conclusion. So let's go back to where we started. You press your hand on the table. You feel its solid surface. But now you know what's really happening. The fuzzy, probabilistic electron clouds of your skin are getting incredibly close to the electron clouds of the table. A huge electromagnetic force flares up between them, the collective scream of trillions of electrons telling each other to back off. Your nerves detect that force, and your brain creates a simplified, useful lie: touch. This completely reframes our connection to the world. If touch is just feeling a force at a distance, what about our other senses? The light hitting your eyes is just you interacting with the electromagnetic field from the screen. The sound you hear is just your eardrum interacting with pressure waves created by air molecules repelling each other. All of our senses are just different ways of interpreting interactions with fundamental fields. We're not separate things bumping into a solid world. We are the world, complex patterns of fields and forces constantly interacting with other patterns of fields and forces. This raises a dizzying question. If the chair you're sitting on is just a swarm of probability clouds held together by forces, and you are also a swarm of probability clouds held together by forces, where, exactly, do you end and the chair begin? The idea of a hard boundary just vanishes. There isn't a line. There's a gradient, a zone of interaction. The boundary between you and the world isn't a place, it's a point of intense negotiation between forces. The very concept of a solid object starts to look like a convenient label our brains use for a stable pattern of energy. This doesn't mean the world isn't real. The chair is real. The force it exerts on you is definitely real. If you doubt that, try jumping off a building. The pavement will interact with you very, very forcefully. Solidity isn't a lie. It's just that our intuition for what solidity is wrong. It isn't about being full. It's about being governed by powerful, unbreakable rules. In a strange way, this quantum view is even more intimate than the old one. The old view was of sterile billiard balls bumping into each other. The new view is of interpenetrating fields, of your atomic force fields reaching out and communicating with the force fields of the world around you. So, the next time you hold a loved one's hand, take a second to appreciate what's really going on. Your atoms and their atoms are maintaining that microscopic, uncrossable gap, held apart by the laws of the universe. No particle from your hand will ever touch a particle from theirs. But across that tiny void, your electron fields are pushing against theirs. You are feeling one of the four fundamental forces of the cosmos. You're not just touching a hand. You are directly, profoundly interacting with the very fabric of reality. You aren't touching, you're connecting. Why everything you touch is about to disappear. Look around you, right now. That chair you're sitting on, the phone in your hand, the floor beneath your feet, they all feel solid. Real. They have weight and substance. Knock on your desk and you hear that satisfying thud. This is the world as you know it. But what if I told you that's an illusion? A beautiful, profound illusion your senses have been tricked into believing. Because in reality, everything you think of as solid is in a constant, desperate struggle to keep from falling apart. At any moment, it could melt into a puddle or just vanish into thin air. The solid world isn't a permanent state. It's a temporary truce, a fragile peace treaty in an invisible war raging on a scale so small it's almost impossible to imagine. Today, we journey into the heart of that battle. We'll meet the two warring forces whose delicate balance is the only thing holding your world together. The illusion of solidity. Let's start with what feels real: touch. When you press your hand against a wall, what are you actually feeling? You think you're making contact, but you're not. Not even close. What you're really feeling is a force. An invisible shield of pure repulsion. The atoms in your hand are made of a nucleus surrounded by a cloud of negatively charged electrons. The atoms of the wall? They're made of the exact same stuff. And just like two negative ends of a magnet, the electron clouds of your hand and the wall are fiercely pushing each other away. You aren't touching the wall. You are hovering an infinitesimal distance from it, held back by the electromagnetic force. That feeling of solidity is just your brain's interpretation of this colossal, microscopic standoff. Think about that. Every physical sensation you've ever had, the comfort of a bed, the sting of stubbing your toe, holding someone's hand, it's all been based on this useful illusion. You have never truly, physically, made contact with another object in your entire life. There has always been a gap, an empty space, filled only by warring fields of force. And that's just the first crack in the facade. The truly mind-bending instability of our world lies not in the space between things, but in the very fabric of the things themselves. We all learn about the three states of matter: solid, liquid, gas. We watch solid ice melt into liquid water, which then boils away into invisible steam. We see it as a transformation. The ice becomes water. The water becomes steam. But what if we reframe that? What if it's not a transformation, but a asterisk collapse? A structural failure. The solid ice didn't just change. Its internal architecture, the very thing that made it solid, broke. The agreement that held billions of molecules in a fixed, rigid pattern was violated. The structure fell apart into the disorganized chaos of a liquid. Add more energy, and even those loose connections fail, scattering the molecules into the total anarchy of a gas. This is the key. Every solid object around you is held together by a fragile agreement. And that agreement can be broken. The story of matter is the story of this constant, precarious balance between order and chaos. And it's the reason why, under the right conditions, it could all just disappear. The invisible war, a tug of war for reality. So, what is this invisible battle? Who are the two sides? On a fundamental level, the state of all matter is decided by a cosmic tug of war between two opposing forces. On one side, you have the forces of attraction. This is the glue that pulls molecules together, that wants to create structure and order. These are known as intermolecular forces. Think of them as the universe's desire for things to stick together. On the other side, you have kinetic energy. This is the energy of motion. Every atom and molecule in the universe is in constant, frantic motion. They vibrate, jiggle, and zip around. Temperature is just our way of measuring this energy. The hotter something is, the more violently its particles are moving. Kinetic energy is the force of chaos. It wants to tear everything apart. The state of any substance is decided by who's winning this tug of war. If the attractive forces are winning, they pull the molecules into a tight, ordered formation. The particles don't have enough kinetic energy to break free. They're locked into place, only able to vibrate. This is the solid state. If we add energy, heat, we're giving a power up to the other side. The kinetic energy increases. The particles vibrate more and more violently, until they have enough energy to overcome the rigid grip of attraction. They break out of their fixed positions and start sliding past one another. The structure has failed. This is the liquid state. The battle is now a tense draw. If we keep adding energy, the particles move so fast that their kinetic energy completely overwhelms the attractive forces. The molecules break free entirely and fly off in random directions. This is the gaseous state. Kinetic energy has won. So, the rock on your desk isn't solid because it is solid. It's solid because at this temperature, the attractive forces inside it are winning. Change the energy, you change the winner. And when the winner changes, the world as you know it dissolves. The ghost in the machine, unmasking van der Waals forces. So what is this mysterious molecular glue? For most everyday objects, it's not a strong, permanent bond. The forces within a molecule are like superglue. But the forces between one molecule and its neighbor are much, much weaker. They're more like sticky notes. These are collectively known as intermolecular forces, and the most common and strangest of them all is the London dispersion force, a type of van der Waals force. To get this, you have to throw out that old picture of an atom as a tiny solar system. Thanks to quantum mechanics, the reality is far weirder. An electron isn't a little ball in a neat orbit, it's a cloud of probability. A smear of negative charge. Now, picture a simple, balanced atom. On average, its electron cloud is perfectly symmetrical, so the atom is neutral. But, on average, is the key. The electrons are in a constant, random, quantum jitter. And in any given instant, the electrons might just happen to slosh over to one side of the atom. For a fleeting fraction of a second, one side is slightly negative and the other is slightly positive. The neutral atom has become a tiny, weak magnet, an instantaneous dipole. And here's where the magic happens. That temporary positive pull on our first atom gently pulls on the electron cloud of its neighbor. It tugs the neighbor's negative electrons towards it, turning the second atom into a dipole, too, an induced dipole. For one brief moment, you have two tiny magnets lined up, positive to negative. And they attract each other. This fleeting, ghostly attraction is the London dispersion force. A split second later, the electrons slosh back, and the whole process flickers and reforms. It's a constant, shimmering dance of attraction, appearing and disappearing millions of times a second. This is the quantum glue holding our world together. It's not a permanent bond, it's a statistical whisper. It's the cumulative effect of countless tiny, temporary handshakes between molecules. The strength of this glue depends on the size of the molecules. Larger atoms have bigger, floppier electron clouds that are more easily distorted. This quality is called polarizability. A big, squishy electron cloud can form stronger temporary dipoles than the tight electron cloud of a tiny atom. This is why substances made of larger molecules generally have higher melting and boiling points. It takes more kinetic energy to break their stronger collective grip. It's the collective cooperation of trillions of these flickering attractions that creates the solidity of your world. They are the reason a gecko can walk up a wall. The immense number of tiny van der Waals interactions creates a powerful adhesive force. And they are also the reason that solidity is so fragile. Because this glue isn't a permanent weld, it's a probabilistic whisper. All it takes is a little extra energy to drown out that whisper and break the agreement. The battlefield, a journey through the states of matter. Now that we know the two sides, kinetic energy versus the ghostly van der Waals forces, let's take a tour of the battlefield. Let's zoom in and watch this struggle play out in the most familiar substance of all, water. Part 1. The fortress of the solid. Imagine a block of ice, cooled way below freezing. At this low temperature, kinetic energy is minimal. The water molecules are just gently vibrating in place. The attractive forces are in complete command. In water, these attractive forces are a mix, but they're dominated by a particularly strong type of intermolecular attraction called a hydrogen bond. This is a super-powered version of a dipole-dipole force that happens when hydrogen is bonded to a highly electronegative atom like oxygen. The oxygen pulls so hard on the electrons that the hydrogen end of the molecule is left with a strong positive charge and the oxygen end is strongly negative. These powerful attractions lock the water molecules into a highly ordered, rigid crystal lattice. Think of it as a perfectly organized army, with every soldier in formation. Each molecule is held firmly in place by the hydrogen bonds to its neighbors. They can fidget, but they can't leave their post. Their kinetic energy just isn't enough to break the bonds. This is why a solid has a definite shape and volume. The fortress is holding. Part 2. The anarchy of the melt, the liquid state. Now, let's add heat. We are essentially arming the opposition. The kinetic energy of the water molecules rises. They begin shaking violently. The bonds holding them in place stretch and groan. At 0 degrees Celsius or 32 degrees Fahrenheit, a critical threshold is reached, the melting point. The individual water molecules have finally absorbed enough kinetic energy to break free from the rigid crystal lattice. The fortress crumbles, but kinetic energy hasn't won completely. The attractive forces are still powerful enough to keep the molecules from escaping entirely. They can break from their fixed positions, but now they just slide and tumble past each other. This is the liquid state. Imagine the bolts on the army's boots have broken. They can move around and jostle past one another, but they're all still stuck in the same room. The crowd flows and shifts, taking the shape of the room, but the total number of people, the volume, stays the same. The tug of war is now a chaotic stalemate. The great escape, the gaseous state. Let's keep adding energy. We put the water on a stove. The kinetic energy skyrockets. The dance becomes a frantic mosh pit. Molecules at the surface gain enough velocity to completely sever the bonds holding them to their neighbors and launch themselves into the air. This is evaporation. As we approach 100 degrees Celsius, the boiling point, this goes into overdrive. Bubbles of pure water vapor form inside the liquid and rush to the surface. At this point, kinetic energy has achieved total victory. The attractive forces are overwhelmed. The molecules fly off in random directions as a gas we call steam. In our analogy, the walls of the room have been demolished. The soldiers are free to run in any direction, spreading out to fill any space they can. A gas has no fixed shape and no fixed volume. The agreement has been shattered. The structure has completely disappeared. The revelation, disappearance, is a change of perspective. So, what about that promise? That everything you touch is about to disappear? Well, that disappearance is the phase transition. When solid ice melts, its solidity vanishes. When the water boils, its liquid form dematerializes into the air. The object, as we knew it, is gone. The molecules are all still there, but their agreement to stick together has been broken by kinetic energy. This reveals a profound truth. Solidity is not the default state of matter. It's a special, low-energy condition. The exception, not the rule. We live our lives in a tiny sliver of the cosmic temperature range where the delicate forces of attraction can win the tug of war. For us, solids seem permanent. On a universal scale, they are incredibly fragile. Consider dry ice, solid carbon dioxide. At room temperature, it doesn't melt. It goes directly from a solid to a gas. It literally vanishes before your eyes. This happens because its intermolecular forces are so weak that there is no stable liquid phase in our atmosphere. The molecules get just enough energy to break the solid lattice and they immediately achieve escape velocity. The fortress doesn't crumble into a mob, it explodes directly into a diaspora. The chair you're sitting on is a temporary arrangement of molecules. The phone in your hand is a fleeting conspiracy of atoms. They feel permanent only because you exist in the same low-energy bubble they do. But their structure is not an intrinsic property. It is a conditional state, a fragile truce in an eternal war. And that truce can always be broken, pushing the limits beyond the disappearance. So what happens if we keep pumping in energy? We move beyond the familiar and into the truly extreme. Let's take our water vapor and keep heating it to several thousand degrees. The molecules collide with such violence that they don't just break apart from each other. The super-strong bonds within the molecules themselves are torn apart. The hydrogen oxide molecules disintegrate into individual hydrogen and oxygen atoms. But we can go further. With even more energy, the collisions become so cataclysmic that they knock electrons right out of the atoms. The very architecture of the atom is shattered. What's left is a searingly hot soup of positively charged ions and free, negatively charged electrons. This is plasma, the fourth state of matter. If solid is a fortress, liquid a riot, and gas a diaspora, plasma is a civil war where the citizens themselves have been dismembered. And while it seems exotic, over 99% of the ordinary, visible matter in the cosmos is plasma. Every star, including our sun, is a giant ball of plasma. What about the other direction? What if we remove almost all the kinetic energy, approaching the theoretical limit of absolute zero? Down here, in the ultra-cold, matter gets truly weird. New states emerge, like Bose-Einstein condensates. Here, a cloud of atoms, cooled to within a billionth of a degree of absolute zero, stops behaving like individual particles. Their wave-like quantum natures overlap and merge until they all act as one giant, superatom. The distinction between one atom and the next literally dissolves into a single, collective quantum entity. This journey to the extremes proves our point. The world we see is entirely a product of the energy it contains. Add energy, and a solid disappears into a liquid. Add a lot more, and the very atoms that make it are ripped apart. The world isn't made of things, it's made of energy states. Conclusion. So, look around you one more time. The desk, the walls, the cup of coffee. They look the same, but they aren't. Because you've seen the silent, invisible war that defines them. You're witnessing a universe of temporary truces. Every solid thing is a testament to the quiet victory of attraction over motion. Every liquid is a beautiful, swirling stalemate. The air you breathe is a celebration of freedom. You now know that touch is an illusion of repulsion, and solidity is a fragile agreement between trillions of flickering, quantum forces. The world isn't a collection of nouns, it's a collection of verbs. It is a dynamic, energetic dance of forces. And understanding that conflict changes everything. It transforms the mundane act of ice melting in a glass into a profound drama of structural collapse. The world is not as it seems. It is so much more intricate, more fragile, and more wonderful. If this journey into the secret life of matter sparked your curiosity, subscribe and join our community of explorers. What everyday things do you see differently now? Let us know in the comments below. Why creating this superfuel keeps destroying diamonds. There is a state of matter, predicted by physics nearly 100 years ago, that has never been held in a stable form on Earth. It begins with hydrogen, the simplest and most common element in the universe. And it promises to be a material that could allow us to travel between planets in a fraction of the time, and to build power grids with zero energy loss. Scientists know what it's made of. They have a good idea of how to make it. There's just one problem. To create this material, they must take a flawless diamond, the hardest substance we know, and intentionally, repeatedly, crush it. This isn't a mistake in the process, it is a fundamental part of it. It's a paradox that makes this scientific quest one of the most challenging in modern physics. This is the story of metallic hydrogen, a substance that could change our world, but only if we can understand why the journey to create it demands the sacrifice of the very tools needed to make it. The answer takes us to the absolute limits of pressure and reveals a quiet battle between the smallest atom and the strongest material. The promise, the what, and why. To understand why scientists are willing to destroy some of the most perfect materials on the planet, we first need to look at the predicted properties of metallic hydrogen. And to do that, we have to start with the basics. Hydrogen, a single proton and a single electron. It is the fuel of stars. Here on Earth, it exists as a transparent gas, with two atoms bonded together to form a molecule, H2. In this form, it's everywhere, but it is largely unremarkable. But for almost a century, physicists have been thinking about a prediction made in 1935 by Eugene Wigner and Hilliard Huntington. They wondered what would happen if you could take this simple gas and subject it to immense pressures greater than those at the center of the Earth. Their calculations suggested something remarkable would happen. If you could squeeze hydrogen molecules close enough together, the bonds holding them in pairs would break. The atoms themselves would be forced so near to one another that their electron clouds would overlap and merge. At this point, the electrons would no longer be tied to a single proton. They would be free to move across the entire structure of hydrogen atoms. In that moment, hydrogen would stop being a gas. It would transform into something never seen in a stable form on our planet: a dense, solid, atomic metal. This transformation is the basis for a material with properties so unusual they would open up new possibilities for technology. The search for metallic hydrogen isn't just for scientific curiosity, it's a search for two long-sought technologies. The first is its potential as a powerful chemical rocket propellant. The performance of a rocket fuel is measured by its specific impulse, or ISP. It's like a measure of efficiency. A higher number means more push for the same amount of fuel. The engines of the Space Shuttle, using liquid hydrogen and oxygen, had a specific impulse of around 450 seconds. The best chemical fuels we have today reach about 500 seconds. Metallic hydrogen, if it proves to be metastable, meaning it remains solid after the pressure is removed, is predicted to have a specific impulse between 1000 and 1700 seconds. This isn't a small improvement. The energy released when it transitions back into a gas would be over 20 times that of standard rocket fuels. A rocket with this fuel could potentially reach orbit in a single stage. Journeys to Jupiter that now take more than 5 years could be reduced to just a few months. The second potential application is as a room-temperature superconductor. A superconductor is a material that conducts electricity with zero resistance, meaning no energy is lost as heat. The problem is, all known superconductors only work at extremely cold temperatures, which makes them expensive and difficult to use widely. A room-temperature superconductor is one of the great goals of materials science. It would mean lossless power grids, saving the estimated 15% of energy currently wasted during transmission. It would allow for powerful magnets for new kinds of high-speed trains or more efficient MRI machines. It could also form the basis for new types of quantum computers. This isn't just theory. Metallic hydrogen is thought to already exist in the universe. The immense pressures inside gas giants like Jupiter and Saturn are believed to be the natural environment where it forms. Scientists think the powerful magnetic fields of these planets are generated by moving currents of this metallic hydrogen deep inside them. Creating it in a lab is about more than making a new material. It's about recreating the conditions at the heart of another planet to study the physics that governs our solar system. A new propellant, a perfect conductor, and a window into other worlds. This is the promise of metallic hydrogen. The forge, the how. How do you create pressures greater than the Earth's core within a laboratory? The instrument used for this is not a massive machine, but a small and precise device called a diamond anvil cell, or DAC. To understand how it works, you have to understand pressure. Pressure is force concentrated over an area. A thumbtack is a good example. You can press on the flat head with your thumb and feel very little discomfort. But that same force, when concentrated on the tiny point, is enough to push it into wood. The force is the same, the pressure is immense. The diamond anvil cell is a refined expression of this principle. The device can often fit in the palm of your hand. At its center are two flawless, gem-quality diamonds. These are not jewelry, they are engineered for their purity and lack of internal flaws. They are cut not to sparkle, but to focus force. The back of the diamond is a wide, flat surface, while the front is polished down to a microscopic point called a culet, sometimes only a few micrometers wide. The experiment is a precise process. A thin metal ring, the gasket, is placed between the two diamond tips. It has a tiny hole drilled in its center to serve as a sample chamber. A small amount of hydrogen is loaded into this chamber. Often, a tiny chip of ruby is also placed inside. The ruby acts as a pressure gauge. By shining a laser on it and measuring the change in its fluorescent light, scientists can calculate the exact pressure inside. Once it's sealed, a scientist begins to turn the screws on the device. This applies a manageable force to the large, flat backs of the diamonds. That force is then channeled down to the microscopic tips. The amplification is immense. A small mechanical force becomes pressures of hundreds of gigapascals. For perspective, the experiments for metallic hydrogen aim for pressures between 400 and 500 gigapascals, which is a pressure greater than that at the core of the Earth. All of this is generated in a handheld device. This is why diamonds are necessary. Diamond is the hardest material we know. Its rigid crystal structure of carbon atoms can withstand these enormous stresses without deforming. Any other known material would break or bend long before reaching these pressures. Scientists watch through microscopes as they slowly increase the pressure, sometimes using a laser to heat the sample through the transparent diamond, trying to find the exact conditions for the transformation. This entire field of study began with pioneers like Percy Bridgman, who received a Nobel Prize in 1946 for his work on high-pressure devices, laying the foundation for the modern DAC. For decades, the goal has been metallic hydrogen, and the diamond anvil is the primary tool for the task. The conflict, the diamond problem. For a long time, creating metallic hydrogen was a distant goal. Then, in 2017, a team at Harvard University, led by Isaac Silveira and Ranga Dias, made an announcement. In a paper in the journal Science, they claimed to have succeeded. Their evidence was a photograph of the sample in their diamond anvil cell. At a pressure of 495 gigapascals, the transparent hydrogen had become reflective. It looked like a metal, just as the theory predicted. It seemed the decades-long search was over. But the claim was difficult to verify. Shortly after the observation, the sample was lost. The diamond anvils failed. With a crack, one of the diamonds shattered, the pressure was released, and the microscopic piece of metallic hydrogen was gone. Did it remain metallic, a tiny speck lost in the device? Or did it simply turn back into a gas? Without the sample, there was no way to know. Other labs expressed doubts. Some questioned the pressure measurement, while others noted that a coating of alumina used on the diamonds could have been responsible for the reflective signal. The claim rested on a single experiment that ended with the destruction of the equipment, making it hard for many in the community to accept. The story became more complex later on. Ranga Dias, after moving to the University of Rochester, published other remarkable claims about superconductivity. But several of his major papers were later retracted after investigations found falsified data, and he left the university. This cast a further shadow on the original 2017 claim. This story highlights the central conflict in this research: the diamonds themselves. Isaac Silveira has noted how frequently the diamonds break at these pressures. A French research team reported breaking many sets of diamonds trying to reach high pressures. This failure is not an accident, it is almost an expected outcome. Why does the hardest material on Earth keep shattering? There are two main reasons. The first is simply the immense force. Even a diamond has a breaking point. Under these conditions, any microscopic imperfection can become the start of a crack that instantly destroys the anvil. The second reason is more subtle. It's a phenomenon known as hydrogen embrittlement. Hydrogen is the smallest atom. Under extreme pressure, these tiny atoms can be forced into the diamond's own crystal lattice. Imagine the diamond as a perfect, repeating structure. The hydrogen atoms work their way into tiny gaps, creating stress from within and weakening the material. The diamond might look fine, but it has been internally compromised. Then, at peak pressure or with a change in temperature from a laser, the weakened structure gives way and the diamond breaks apart. Researchers describe it as a sharp ping, the sound of months or years of work disappearing along with an instrument worth tens of thousands of dollars. This is the difficult cycle of the research. To create metallic hydrogen, you need pressures that are at the breaking point of diamond. But the hydrogen itself appears to weaken the diamond, lowering that breaking point. The material they are trying to create actively works against the tool they are using to create it. It is a quiet, fundamental conflict between the smallest atom and the hardest material. This constant destruction seems like an impasse. But scientists are persistent. They have developed clever ways to work around this problem. If you're interested in these kinds of deep dives into the edges of physics, consider following our channel for more stories like this. The fight back, new strategies. Faced with an experiment where the anvils are almost a disposable part, physicists have developed creative strategies. The search for metallic hydrogen has become a story of ingenuity. The first strategy is to protect the diamonds. This is what the Harvard team attempted by applying a thin coating of aluminum oxide, or alumina, to their diamond tips. This coating acts as a barrier to keep hydrogen atoms from getting into the diamond lattice. It may have helped them reach their record pressures, but it also created ambiguity in their results. It's a common trade-off in experiments. Solving one problem can sometimes introduce another. A second approach changes the conditions of pressure and temperature. Instead of just squeezing the sample at cold temperatures, many teams now use lasers to heat it in short, powerful pulses. This added heat can help the hydrogen transition to a metallic state at slightly lower pressures, which are safer for the diamonds. This combination of static pressure and pulsed heating is also interesting to planetary scientists, as it more closely mimics the conditions inside giant planets. Some researchers, however, have turned to a different method entirely: dynamic compression. At places like Lawrence Livermore National Laboratory, scientists use large two-stage gas guns. These devices fire a projectile at several kilometers per second into a target containing liquid hydrogen. The impact creates a powerful shockwave that compresses and heats the hydrogen for a few billionths of a second. The pressures can be even higher than in a DAC, but the challenge is collecting reliable data in such a short amount of time. It provides an alternative path, one based on a sudden shock rather than a slow squeeze. Beyond new techniques, scientists are also studying new materials. The difficulty of working with pure hydrogen has led some to an interesting idea. What if you pre-compress the hydrogen chemically? This is the focus of research into hydrogen-rich compounds called hydrides. By bonding hydrogen with other elements, like lanthanum or yttrium, you trap hydrogen atoms in an already dense structure. The idea is that this chemical precompression means you need less physical pressure to make the hydrogen metallic and superconducting. This line of research, while also complicated by the retracted papers, remains a promising area of study. All of these explorations show that matter behaves in strange ways under pressure. At similar pressures, carbon dioxide transforms into a quartz-like solid. Scientists have found over 20 different phases of ice, including one that can exist at room temperature if the pressure is high enough. These discoveries remind us that our everyday experience of materials is just one small part of what is possible. The future, what's next on the quest? So, where does the search stand today, in early 2026? After a period of dramatic claims and retractions, the field has entered a more cautious phase. The scientific consensus is that no one has yet produced a stable, verified sample of metallic hydrogen that can be studied outside of a pressure cell. The goal remains elusive. The controversies have, in a way, been useful. They have led the community to require a higher standard of proof for future claims. A single photograph or sensor reading is no longer enough. Future claims will need multiple, independent lines of evidence that can be reproduced by other labs. Researchers continue to refine their tools. New diamond anvil designs are being tested, some with different shapes that might distribute stress more effectively and allow for even higher pressures. At the same time, general interest in the hydrogen economy continues to grow, and while mostly focused on hydrogen gas, this broad interest could benefit fundamental research. But even with these advances, the most important questions about metallic hydrogen are still unanswered. The first is the question of metastability. If you create metallic hydrogen at 500 gigapascals and then release the pressure, will it stay metallic? Some models predict that it will, much like a diamond remains a diamond after being formed under pressure. If so, its use as a rocket fuel is a real possibility. But other models predict it will not be metastable, and that it would instantly revert to a gas. The first team to create a verifiable sample and answer this question will define the future of the field. The second question is what pressure is actually needed. The theoretical predictions have shifted over the years. Is it 450 gigapascals? 495 gigapascals? Or is it even higher? Until it is made and confirmed, the exact target is uncertain. Finally, there is the problem of the diamonds themselves. There may be a limit to how far diamond anvil technology can be pushed. The creation of metallic hydrogen might require a completely new class of super-hard materials that haven't been invented yet. The search for this material is also a search for tools that are even stronger than diamond. The path forward is slow and difficult, requiring more robust data and transparent work. The quest has not failed. It has just proven to be one of the most difficult challenges in experimental physics. Conclusion: the journey to create metallic hydrogen begins with a simple question. What happens when we squeeze the simplest element as hard as we can? That question leads to an incredible promise: a propellant for space travel and a superconductor for our world. To chase that promise, scientists built a modern forge, the diamond anvil cell, a small device that can create the pressure at the center of a planet. But inside that forge, they found a fundamental conflict, a struggle where the hardest material we know is broken by the smallest atom. For now, metallic hydrogen remains just out of reach, a prediction tangled in the real-world challenges of experimentation. But the quest is defined by its persistence. Every broken anvil is a lesson. Every retracted paper is a reminder of the need for rigor. This work pushes the boundaries of what we know, forcing us to invent new techniques and new ways of thinking about matter. The hunt for metallic hydrogen is more than a race for a new material. It's a testament to the process of exploring the unknown, of recreating the universe's most extreme environments to see what secrets are hidden there. It stretches the idea of what matter can be. What do you think is the most interesting potential for metallic hydrogen? Its use in space travel or as a room temperature superconductor? Let us know your thoughts in the comments below. The journey to where structure breaks. What if we could take a piece of matter and just push it? Not a gentle nudge, but a relentless, cosmic-scale assault. What if we could heat it, squeeze it, and blast it with energies so extreme that its very structure starts to come apart at the seams? We're not talking about just melting ice or boiling water. We're talking about a journey to the absolute ragged edge of reality, a trip past the familiar states of matter into a bizarre realm where the rules of our universe get twisted, shattered, and ultimately, broken. What happens when the fundamental building blocks of everything we are, and everything we see, are literally torn apart? This isn't just a thought experiment. This is a headfirst dive into the heart of physics, a journey to find the ultimate breaking point of matter itself. Look around you. Everything, the chair you're in, the screen you're watching, the very air you breathe, it all has structure. That structure is held together by a delicate dance of forces, a cosmic rulebook for how to build a universe. But what happens if we start cranking up the energy? What if we take a simple crystal of ice and begin a campaign of pure, focused violence against its very being? We're going to follow this crystal as we turn up the universal thermostat, climbing a ladder of destruction that will take us from the everyday to the utterly surreal. We'll see not just one breaking point, but a whole series of them, each one more profound than the last. This journey will take us through fire, into the core of stars, and to the very first moments of time. So, get ready. We're about to find out what happens when you push the fabric of reality until it rips. The familiar world of order. Our journey starts with something simple and elegant, a crystal. Let's picture a perfect crystal of water ice, chilled to near absolute zero. At this temperature, about as cold as anything can get, all the atomic jitters nearly stop. The water molecules are locked into a beautiful, repeating 3D pattern, a crystalline lattice. That's what makes a solid, well, solid. Its particles are packed tight in fixed spots, giving the material a definite shape and volume. Each water molecule, with its 2 hydrogen atoms and 1 oxygen, is connected to its neighbors by hydrogen bonds. Think of these bonds as powerful, invisible springs linking each molecule to the ones around it. This network of springs creates a rigid, stable structure. This is order. This is the foundation of the world we can touch and feel. All the properties we take for granted, hardness, shape, stability, come from this microscopic arrangement. The force running the show here is the electromagnetic force, one of the 4 fundamental forces of nature. It's the force that dictates how charged particles interact. In our ice crystal, the slightly positive hydrogen atoms of one molecule are attracted to the slightly negative oxygen atoms of another. Countless tiny attractions, all working together, create the solid state. They're the glue of our everyday world. But structure is a delicate thing. It's a state of low energy, of calm. It only exists because the forces holding it together are stronger than the energies trying to tear it apart. For now, in our super chilled ice crystal, everything is quiet. But we're not here to admire stability. We're here to break it. Our journey begins by adding the one thing that all structures fear: energy. We're going to start heating our crystal. We're about to launch a direct assault on the bonds holding this beautiful lattice together and witness the first, and most familiar, breaking point. The first break: melting and boiling. We start adding heat. Heat is just energy in motion, and as we pump it into our ice crystal, the water molecules absorb it and start to vibrate more and more violently. Those invisible springs holding the lattice together are stretched almost to their breaking point. Imagine a perfectly ordered formation of soldiers. Now, imagine the ground starts to shake. At first, they can hold their positions, but as the shaking gets worse, they start to bump and jostle each other. The perfect order decays into chaos. That's exactly what's happening inside our crystal. The thermal energy we're adding is fighting directly against the electromagnetic forces. The vibrations get so intense they start to overpower the hydrogen bonds locking the molecules in place. At a specific temperature, 0 degrees Celsius, 32 degrees Fahrenheit, we hit a critical point, the melting point. Suddenly, entire clusters of molecules have enough energy to snap free from their fixed positions. The rigid lattice collapses. The long-range order is gone. Our crystal, once hard and defined, slumps into a puddle of liquid water. We've just witnessed a phase transition, a fundamental change in the structure of matter. We've made our first break. In a liquid, the particles aren't locked down anymore. They can slide past one another, which is why liquid flows and takes the shape of its container. They're still close, held together by weaker forces, but the disciplined army has turned into a dense, jostling crowd. But we're not done. Not even close. What happens if we keep adding heat? The molecules in the water keep absorbing energy, moving faster and faster, and colliding with more force. At the surface, some molecules gain enough of a kick to escape entirely. That's evaporation. As we crank the heat up to 100 degrees Celsius, 212 degrees Fahrenheit, the boiling point of water, this process goes into overdrive. At the boiling point, molecules throughout the liquid now have enough energy to completely sever the last tethers holding them to their neighbors. Bubbles of water vapor, a gas, form inside the liquid and race to the surface. Our dense crowd of molecules is now scattering, with each individual bolting off in a random direction. The matter has become a gas. In the gaseous state, the particles are far apart, moving chaotically and expanding to fill any container you put them in. All the bonds between molecules have been broken. The structure that once defined our crystal is completely gone, leaving only individual water molecules zipping around at high speed. We started with a solid, a state of perfect order, and broke it down twice, first to a liquid, then to a gas. This is the journey of matter we all learn about in school. But for us, this is just the warm-up. The structure of the asterisk crystal is gone, but the structure of the asterisk molecules is still there. Each particle of steam is still a water molecule, 2 hydrogens bonded to 1 oxygen. So, we have to ask the next question. What happens if we go even further? What happens when we heat this gas to temperatures far beyond anything on Earth? We're about to cross into a state of matter so extreme it makes up 99% of the visible universe, yet is almost never found on our planet. We're about to break the atom itself. The point of no return, entering the plasma. We now have a container full of superheated water vapor. The molecules are chaotic and free, but we're relentless. We keep pumping in energy, raising the temperature by thousands of degrees. At these ferocious temperatures, the collisions between water molecules become unbelievably violent. We're not just making them move faster anymore, we're smashing them into each other so hard that the molecules themselves break apart. The chemical bonds holding the hydrogen and oxygen atoms together are shattered. Our container is now filled with a hot gas of individual hydrogen and oxygen atoms. But we don't stop. We crank the dial even higher. Thousands of degrees become tens of thousands. Now, something truly profound happens. Atoms are made of a dense nucleus surrounded by a cloud of electrons. As they absorb this incredible energy, the electrons just can't hold on anymore. The sheer violence of the environment is too much for the electromagnetic force that binds the electrons to their nuclei. One by one, the electrons are stripped away. They're torn from their orbits, leaving behind a positively charged atom, now called an ion. We've just triggered ionization. Our gas of neutral atoms is morphing into a seething, electrically charged chaos. This is the 4th state of matter, plasma. Plasma isn't just a hot gas. Its defining feature is that it's made of charged particles, free-roaming electrons and positive ions, moving independently. This electrified gas is fundamentally different from the other 3 states. Because its particles are charged, it can conduct electricity and is violently reactive to magnetic fields. It's no longer a collection of neutral particles. It's a dynamic, turbulent soup of raw electrical charge. We see plasma all the time. A jagged bolt of lightning is just a channel of air heated so intensely it becomes plasma. The soft glow of a neon sign is a tube of gas turned into a plasma by electricity. The northern and southern lights are dazzling curtains of plasma, created when particles from the sun slam into our upper atmosphere. And when we look out into the cosmos, plasma is the rule, not the exception. Our sun, and every star, is a giant ball of plasma. The incredible heat and pressure in their cores guarantee that all matter exists in this ionized state. In fact, over 99% of all the visible matter in the universe is plasma. The solid, liquid, and gas that make up our world are, from a cosmic perspective, an incredibly rare exception. As we keep cranking up the temperature of our plasma, more electrons are stripped away. At the temperatures you'd find inside a star, all the electrons are liberated, creating a fully ionized plasma. A roiling sea of bare atomic nuclei swimming in a swarm of their former electrons. We've now achieved a truly fundamental break. We didn't just break the bonds between molecules, we've broken the atoms themselves apart. But even here, in this stellar furnace we've created, there's still structure. The nuclei of hydrogen and oxygen, though stripped bare, are still intact. A hydrogen nucleus is still a proton. An oxygen nucleus is still a bundle of protons and neutrons. The structure of the atom is gone, but the structure of the asterisk nucleus remains. And that structure is held together by a force far, far more powerful than the electromagnetism we just defeated. To continue our journey, to find the next breaking point, we have to declare war on the strongest force in the known universe. The heart of the atom. Our container is now filled with an ultra-hot plasma, a swarm of electrons and bare atomic nuclei. To go further, we have to zoom in on the impossibly dense core of an atom, the nucleus. Let's pick one of the oxygen nuclei. It's a tightly packed ball of 8 protons and, usually, 8 neutrons. Here, we run into a huge problem. Each of those 8 protons has a positive charge, and like charges repel. The electromagnetic force, the same one that holds our world together, is trying to blow this nucleus apart with incredible intensity. So, what holds it together? The answer is the strong nuclear force. It's the most powerful of the 4 fundamental forces, about 100 times stronger than electromagnetism at these tiny distances. It's the glue that holds the nucleus together, easily overpowering the electromagnetic repulsion between the protons. But the strong force is weird. Unlike gravity or electromagnetism, which have an infinite reach, the strong force only works over incredibly short distances, about the width of a single proton. If you pull 2 protons or neutrons, known as nucleons, slightly apart, the strong force actually gets stronger, like a cosmic rubber band. But if you pull them too far, the force suddenly drops to 0. It's an incredibly powerful but short-leashed giant. This force, however, is just a shadow of what's really going on. To see the true strong force, we have to go even deeper and break open the very particles we thought were fundamental. Protons and neutrons aren't elementary. They're each made of 3 even smaller particles called quarks. A proton has 2 up quarks and 1 down quark. A neutron has 1 up and 2 down quarks. These quarks are what really feel the fundamental strong force, which is carried by particles called gluons, and yes, they're named that because they literally glue the quarks together. This whole interaction is described by a theory called quantum chromodynamics, or QCD. In QCD, quarks have a property called color charge, which has nothing to do with visible color. It's a type of charge, and there are 3 kinds: red, green, and blue. The unbreakable rule of the universe is that you can't have a particle with a net color charge floating around. You can only have color-neutral combinations, like a trio of red, green, and blue quarks together in a proton or neutron. This leads to a bizarre phenomenon called color confinement. The force between 2 quarks doesn't get weaker with distance, it stays constant. It's as if they're connected by a string of gluons. If you try to pull 2 quarks apart, you just keep pouring energy into the gluon field between them. You can pull and pull, but you will never, ever isolate a single quark. Why? Because eventually, you'll have pumped so much energy into the string that it becomes easier for the string to snap. When it does, that energy instantly creates a new quark and antiquark pair, following E equals mc squared. Instead of 1 free quark, you just end up with 2 new, color-neutral particles. This is why we've never seen a free quark in nature. They are eternally locked inside their proton and neutron prisons. Unbreakable prisons, that is, under normal conditions. We've now arrived at the ultimate challenge. We've broken molecules and we've broken atoms. Now, we're staring at the nucleus and the protons and neutrons inside, held together by the strongest force there is. To continue, we must do the impossible. We have to shatter the protons and neutrons themselves and set the quarks and gluons free. To do that, we'll need temperatures and energies not seen in our universe for 13.8 billion years. The ultimate breakdown, quark-gluon plasma. To break color confinement and melt protons and neutrons, we need an unimaginable amount of energy. We need to create a temperature not of millions, but of trillions of degrees. The theoretical boiling point for hadrons is called the Hagedorn temperature, which is around 2 trillion Kelvin. At this point, the very ideas of proton and neutron stop making sense. How on earth do we do that? Not in a container. No material could possibly survive. We have to do it in the only place we can focus that much energy. A particle accelerator. Welcome to CERN, home of the Large Hadron Collider, LHC. Here, scientists accelerate not just protons, but entire lead nuclei. Lead atoms stripped of all their electrons, to 99.9999991% of the speed of light. Two beams of these ions are shot in opposite directions around the 27-kilometer ring and then slammed into each other inside massive detectors, like the Alice experiment. In the fleeting instant of impact, the hundreds of protons and neutrons from the two nuclei collide. The energy density becomes so immense and the temperature soars so high that for a fraction of a second, a minuscule fireball is created. In August 2012, experiments at Alice recorded a temperature of around 5.5 trillion Kelvin. For a brief moment, this was the hottest spot in the known universe, far hotter than the core of any star. And inside that fireball, the impossible happens. The protons and neutrons melt. The incredible energy density overwhelms the strong force's confinement. The boundaries of individual protons and neutrons dissolve, and for a period lasting only about 10 to 23 seconds, the quarks and gluons are deconfined. They're no longer trapped in their three quark prisons. They are free. This is it, the fifth state of matter. This is quark-gluon plasma, QGP. It's often called quark soup, and it's believed to be the state that filled the entire universe for the first few microseconds after the Big Bang. By creating QGP, scientists at CERN and other facilities are literally recreating the conditions of the infant universe in a lab. So what is this stuff actually like? Scientists first thought it would be like a gas of free quarks. But experiments showed something shocking. QGP behaves not like a gas, but like a nearly perfect liquid, with extremely low viscosity. This means it flows with almost no friction, more perfectly than any other fluid known to exist. It's a dense, flowing, incredibly hot liquid of fundamental particles. We have finally done it. We have pushed matter to the point where its most fundamental building blocks, protons and neutrons, have disintegrated. Structure, as we know it, is gone. We are in a realm governed by the raw, naked laws of quantum chromodynamics. It seems like this must be the end of the road. How do you break a fundamental particle like a quark? But the universe is always more creative and more terrifying than we imagine. In the unimaginable pressures of this primordial soup, another, stranger possibility emerges. A transformation that could create the most dangerous substance in the universe. The edge of reality, strange matter. So, we're swimming in the quark-gluon plasma. This perfect liquid of up quarks, down quarks, and gluons that filled the early universe. But the particle zoo has more than just two types of quarks. There are 6 in total. Up and down, charm and strange, and top and bottom. Normally, making heavier quarks like the strange quark costs a lot of energy, and they decay into lighter up and down quarks almost instantly. But inside the ultra-dense and energetic QGP, or maybe in the even more extreme core of a neutron star, a wild theory emerges. What if, under immense pressure, it actually becomes more energy efficient for some of the up and down quarks to transform into strange quarks? This would give rise to a new, theoretical state of matter. A roughly equal mix of up, down, and strange quarks. This is strange matter. According to the strange matter hypothesis, this three-flavor mix might be even more stable than the normal two-flavor matter that makes up you, me, and everything we know. Think of it this way. In a normal nucleus, the up and down quarks are all fighting for the lowest energy states. By introducing a third type of quark, the overall energy of the system can actually be lowered, making the whole thing more stable. If this hypothesis is true, the implications are staggering. Imagine a tiny, microscopic speck of this strange matter, called a strangelet. It would be the most stable possible arrangement of quarks. If this strangelet were to touch a normal atomic nucleus, it wouldn't just bounce off. It would start to convert it. The strong force would trigger a chain reaction, transforming the up and down quarks of the normal matter into strange quarks, absorbing the nucleus into the growing strangelet. The process would release energy and continue, converting any normal matter it touches into more strange matter. Theorists have proposed the existence of strange stars, colossal, city-sized strangelets made entirely of strange matter. If a piece of one ever broke off and traveled through the cosmos, it would be the ultimate cosmic plague, a seed of hyper-stable matter converting anything it met into a lifeless husk of more strange matter. Now, it's really important to say that strange matter and strangelets are purely hypothetical. Experiments have looked for them and found nothing, suggesting that the conditions to make them, perhaps a combination of extreme density and high temperature, might not exist anywhere in the universe today. But the mere possibility forces us to confront a chilling idea. What if the matter we're made of is only metastable? Like a house of cards waiting for a single nudge, our reality might be perched just above a deeper, more stable, and utterly alien state of existence. We've now gone past just breaking structure to questioning its very stability. Is there anywhere left to go? Is there a final, absolute breaking point? To find out, we have to take our journey to its logical, and completely insane, conclusion. We have to ask, what is the absolute hottest anything can possibly get? Beyond breaking, absolute hot? Our journey has been a relentless climb up the energy ladder. With each step, we've broken another layer of structure. But does this ladder go on forever? Is there an absolute hot, like there's an absolute zero? According to our current understanding of physics, the answer is a theoretical yes. This is the Planck temperature. The Planck temperature isn't something we can ever achieve. It's a theoretical limit derived from the fundamental constants of nature. The value is roughly 1.4 times 10 to the 32 Kelvin. That's a 1 followed by 32 zeros. To call this number big is an understatement. It's the temperature the universe is thought to have been at just 1 Planck time, about 10 to the power of minus 43 seconds, after the Big Bang. So, what happens at the Planck temperature? This is where our current theories of physics completely and utterly break down. As you heat something, it glows, emitting thermal radiation. The hotter it gets, the higher the energy of that radiation. At the Planck temperature, particles would be so energetic that the photons of radiation they emit would each be so unbelievably energetic that if you packed that much energy into a tiny enough space, you'd create a microscopic black hole. At the Planck temperature, the fabric of spacetime itself would begin to boil. The universe would become a chaotic quantum foam of microscopic, virtual black holes constantly popping in and out of existence. Particles wouldn't just be energetic, they would be tiny black holes. And at this energy scale, something else is predicted to happen. Gravity, the force we've mostly ignored on our journey, would become just as strong as the other three fundamental forces. It's theorized that at this point, all four forces would unify into a single, primordial superforce. This is the wall. This is the point where general relativity, our theory of gravity, and quantum mechanics, our theory of particles, stop working. They give us gibberish. We have reached the edge of our knowledge, the point where a new theory, a theory of quantum gravity, is needed to describe what happens next. What is beyond the Planck temperature? We genuinely do not know. Does temperature even mean anything past this point? Does spacetime itself dissolve? These questions are at the absolute frontier of physics. We have arrived at the final breaking point, not of matter, but of the very laws that govern it. The structure of physics itself has torn apart. Our journey from an ice crystal to the quantum foam of spacetime has been a wild ride. We've seen that reality is layered, and that each layer of structure can be broken with enough energy. These ideas push our imagination to the limit and represent the deepest questions physicists are tackling today. What do you think lies beyond the Planck temperature? Is it a true end, or just a door to a new kind of physics we can't even imagine yet? Let us know what you think in the comments. Conclusion: we began with a simple question. What happens when structure breaks? We started with a crystal, a bastion of order, and hit it with more and more energy. We watched it melt into a liquid and boil into a gas. We pushed further, into the fire of plasma, tearing the atoms themselves apart. Then, in the recreated fire of the Big Bang, we saw even protons and neutrons melt into a perfect liquid of free quarks and gluons. From there, we peered over the edge of reality at the terrifying, hypothetical world of strange matter. Finally, we took our journey to its ultimate destination, the Planck temperature. A theoretical inferno where spacetime churns into a foam, particles become black holes, and our understanding of physics comes to a screeching halt. The journey to where structure breaks is more than a story of destruction. It's the story of the universe. It shows that the solid, stable world we see is just one fragile layer in a cosmic hierarchy. Beneath each level lies a deeper, more energetic, and more chaotic reality. By pushing matter to its limits, we don't just learn how things end. We learn how they began, and we glimpse the fundamental nature of everything. The universe, it seems, is built on a foundation of broken rules. And the quest to understand what happens when everything falls apart is, and always will be, at the very heart of science. Scientists found 3 states of matter that defy reality. Think about the world around you. Everything seems to fit into neat little boxes, right? You've got solids, liquids, and gases. The ice cube in your drink is a solid, reliably solid. It has a definite shape and volume. As it melts, it becomes a liquid, taking the shape of the glass. Heat it up more, and it turns into steam, a gas that just expands to fill whatever space it's in. This is the simple trilogy of matter we all learn in school. It's the foundation of our physical world. Solid, liquid, gas. It's the rulebook for everything from the chair you're on to the air you're breathing. For centuries, this model was the bedrock of physics, a complete and satisfying picture of how things work. It gave us a sense of order, a feeling that we basically understood what everything is made of. But that tidy picture? It's profoundly incomplete. It's like trying to write a novel knowing only 3 letters of the alphabet. The universe, it turns out, is far stranger and more creative than we ever could have imagined. Beyond the familiar territories of solid, liquid, and gas lie exotic realms, states of matter so bizarre they feel like they were ripped from the pages of a sci-fi novel. And these aren't just slight variations. They are fundamental breaks from reality as we know it. So, forget what you thought you knew. Forget the neat categories and the simple rules. What if I told you there are materials that can flow without any friction, forever? Liquids that defy gravity itself, climbing the walls of their containers like they're alive? What if I told you that hundreds of thousands of individual atoms can be cooled so low they lose their identities and merge into a single, ghostly entity that acts as one? Scientists are discovering new states of matter that don't just bend the rules of physics, they shatter them. They're finding them in the coldest labs on Earth and in the unimaginable fire of particle accelerators that mimic the birth of the universe. And what they're finding isn't just a scientific curiosity. It could rewrite everything we think we know about reality. Today, we're diving into the impossible. We will explore 3 states of matter that defy reality and, in doing so, reveal some of the deepest secrets of the cosmos. Superfluids, the zero-friction ghost. Our journey into the bizarre begins not with a bang, but with a whisper of impossible cold. We're going to a place just fractions of a degree above absolute zero, the theoretical point where all atomic motion is supposed to stop. That's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. In this realm of extreme cold, something extraordinary happens to one of the simplest elements in the universe, helium. The story starts in the early 20th century, with a scientific race to do something that sounds simple now but was a huge deal then: liquefy helium. Helium is everywhere in the universe, but on Earth, it's slippery. It's so light that our gravity can't hold onto it, so it just escapes into space. The only way to really study it was to get it cold enough to condense into a liquid. A Dutch physicist, Heike Kamerlingh-Onnes, took on this challenge. In his lab, he developed groundbreaking refrigeration techniques, pushing temperatures lower than ever before. And in 1908, he did it. He made the world's first liquid helium. It was a massive win for physics. But the weirdest part was still to come. As Onnes and others studied this new, ultra-cold liquid, they noticed it behaved strangely. At about 2.2 degrees above absolute zero, something changed. Suddenly, the liquid helium, which had been bubbling away like any normal liquid, went perfectly still. Eerily calm. It was as if it had lost all its energy, but it was still a liquid. They called this the lambda point, because a graph of its heat capacity showed a sharp spike that looked like the Greek letter lambda. But the real madness was in its properties. This supercooled liquid, now called helium-2, was a superfluid. Imagine pouring coffee and having it flow with zero friction. No stickiness, no resistance, no viscosity at all. If you could stir a vortex into a bucket of superfluid helium, that vortex would theoretically spin forever, never slowing down. It's a perpetual motion machine in liquid form. But the most stunning, reality-bending trick a superfluid can pull off is how it seems to ignore gravity. If you put a little superfluid helium in an open beaker, it doesn't just sit there. An impossibly thin film, only about 30 nanometers thick, starts to crawl up the inside of the beaker, over the lip, and down the outside, dripping off the bottom until the container is empty. This is called the Raman film, and it happens because the superfluid is trying to reach its lowest possible energy state. With zero internal friction, nothing stops it from spreading out and coating every surface it can find. Then you have the fountain effect. If you take a tube packed with a fine powder, so fine a normal liquid could never get through, and dip it into a bath of superfluid helium, the superfluid leaks right through the tiny pores. If you then gently heat the helium inside the tube, it erupts from the top in a continuous, impossible fountain. The heat creates a pressure difference, and the frictionless superfluid rushes toward the heat, creating a powerful, gravity-defying jet. So, what's going on at the quantum level to create this ghost liquid? Well, it turns out all particles are either fermions or bosons. Fermions, like electrons, are loners. They refuse to be in the same quantum state. Bosons, on the other hand, are social butterflies. They love piling into the same quantum state. And the atoms of helium-4, the most common type, are bosons. As you cool these helium atoms, their quantum nature gets dialed up. Each atom is less like a tiny marble and more like a fuzzy cloud of probability called a matter wave. The colder the atoms get, the larger these matter waves become. At the lambda point, something incredible happens. The matter waves of the individual atoms grow so large they start to overlap, until they all merge into one single, giant matter wave. All the atoms lose their individual identities and start behaving as a single, coherent quantum entity. It's like a massive crowd suddenly moving and thinking as one collective mind. This unified state is what allows for the zero viscosity and frictionless flow. There are no individual atoms to bump into each other. There is only the collective, flowing as one. Superfluidity isn't just a lab trick. Its amazing cooling power is crucial for keeping the superconducting magnets and particle accelerators like the Large Hadron Collider at CERN and in-hospital MRI machines running. But maybe the most mind-bending idea is that the cores of neutron stars, the super-dense husks of dead stars, could be superfluid. The insane pressure could crush protons and electrons into neutrons, which can then pair up to act like bosons and form a vast, star-sized ocean of frictionless matter. Our first step into the impossible showed us a liquid that breaks the rules of friction and gravity. But what happens if we go even colder and force atoms not just to act as one, but to become one? Bose-Einstein condensates, the single, superatom. We've seen what happens when you chill helium until its atoms move in perfect, eerie unison. A liquid that flows forever and climbs walls. But that was just the opening act for an even stranger state of matter, one that was predicted decades before we could ever create it. If a superfluid is like a perfectly synchronized dance troupe, our next state is what happens when all the dancers literally merge into a single being. This is the Bose-Einstein condensate, or BEC, a state of matter so cold and fragile it blurs the line between a collection of particles and a single, giant ghost atom. The idea was born back in the 1920s. An Indian physicist named Satyendra Nath Bose was working on a new way to describe photons, the particles of light. He sent his paper to the most famous scientist on the planet, Albert Einstein. Einstein was blown away. He didn't just help Bose get his paper published, he realized Bose's math could also apply to atoms. Einstein took the idea and ran with it. He predicted that if you could take a gas of bosonic atoms, those same socialite particles from our superfluid, and cool them down to just a hair above absolute zero, something truly remarkable would happen. At these insane temperatures and low densities, the atom's matter waves wouldn't just overlap, they would all collapse into the lowest possible energy state, all at once. They would stop being thousands of individual atoms and instead become a single quantum object, a macroscopic entity described by one single wave function. He had just predicted a fifth state of matter. Imagine a huge stage with trillions of dancers, all doing their own chaotic thing. As the temperature drops, they slow down. Then, at a critical moment, they all freeze and begin to move as one unified mind, every single gesture identical, completely indistinguishable from each other. That is a Bose-Einstein condensate. For 70 years, this was purely theoretical. The tech to reach such temperatures just didn't exist. The challenge was huge. You had to get the atoms incredibly cold without them just clumping together into a plain old solid. The breakthrough came in the 1990s with a 1-2 punch of genius techniques: laser cooling and evaporative cooling. First, scientists use lasers to create optical molasses. They hit a cloud of atoms from all 6 directions with laser beams. The lasers are tuned so that an atom moving towards a beam absorbs a photon, gets a tiny kick slowing it down, and then spits the photon out in a random direction. By doing this millions of times a second, the lasers act like a thick goo that slows the atoms from hundreds of miles per hour to a crawl, cooling them to a few millionths of a degree above absolute zero. But even that isn't cold enough. The final step is evaporative cooling. The atoms are held in a magnetic trap, like a bowl. Scientists then slowly lower the walls of this magnetic bowl. The hottest, most energetic atoms, the ones bouncing around near the top, fly away. It's just like how the hottest water molecules evaporate from a cup of coffee, cooling what's left behind. Then, on June 5, 1995, it happened. A team led by Eric Cornell and Carl Wieman at Gila in Colorado succeeded. Using a vapor of rubidium atoms, they laser-cooled them, then used evaporative cooling to push them past the final threshold. They reached a temperature of 170 nanokelvin, 170 billionths of a degree above absolute zero. Looking at their data, they saw it. A sharp, dramatic peak right at zero velocity. A huge chunk of their atoms had stopped moving on their own and condensed into a single quantum state. They had made the world's first Bose-Einstein condensate. Just months later, Wolfgang Ketterle at MIT made an even bigger one. For this monumental achievement, Cornell, Wieman, and Ketterle won the Nobel Prize in 2001. Creating BECs opened a door to a quantum wonderland. Since the entire thing is described by one wave function, scientists can directly see and play with quantum phenomena on a large scale. It's like a giant magnifying glass for the quantum world. One of the wildest experiments came from Lena Vestergaard Howe's lab at Harvard. Light in a vacuum travels at an astonishing 186,000 miles per second. But what if you could slow it down? Howe's team took a cigar-shaped beck and fired a laser pulse into it. The light gets imprinted onto the atoms. Its information is transferred to the superatom. The light itself is gone, converted into a matter wave that moves through the beck. And it moves incredibly slowly. First, they slowed light down to just 17 meters per second, about the speed of a bicycle. Then, in 2001, they went even further. They sent a pulse of light into the condensate, and while it was completely inside, they switched off a second laser. The light stopped, not slowed down, it came to a complete halt for a full millisecond. Its information was stored as a hologram in the beck. Then, they turned the laser back on. The beck released the information, and the light pulse emerged from the other side, perfectly intact, and shot off again at its cosmic speed limit. They had stored light as matter, and then turned it back into light. The applications for this are staggering. BECs could be used to build atom lasers, which emit beams of coherent matter instead of light. They're already being used to make the most precise atomic clocks in the world and are a key platform for developing quantum computers. By creating BECs in grids of light, scientists can create perfect simulators to model everything from the behavior of new materials to the quantum physics near a black hole. From a liquid that flows without friction, we've arrived at a ghostly cloud of atoms that acts as one and can literally stop light in its tracks. We've journeyed to the coldest temperatures imaginable. But our story isn't over. To find our third state of matter, we have to leave absolute zero behind and travel to the opposite extreme, to temperatures so hot they dissolve the fabric of matter itself. Quark-gluon plasma, the primordial soup of creation. We've explored the absolute depths of cold, where quantum mechanics gets really weird. Now, we need to completely flip the thermostat. We're going from a temperature of billionths of a degree above absolute zero to a temperature of several trillion degrees Celsius. That's over 250,000 times hotter than the core of the Sun. We are leaving the quiet, ghostly world of the quantum cold and entering the violent furnace of creation. We're going back in time to the first microseconds after the Big Bang to see a state of matter so extreme it's called the primordial soup, the quark-gluon plasma. To get this, we need to zoom in. Way in, inside the protons and neutrons that make up the nucleus of every atom. For a long time, we thought protons and neutrons were fundamental. They're not. Each one is made of three even smaller particles called quarks. These quarks are bound together by the strongest force in nature, simply called the strong nuclear force. The particles that carry this force are called gluons, because they literally glue the quarks together. This bond is unlike any other force. Imagine two quarks connected by a gluon. If you try to pull them apart, the force between them doesn't get weaker like gravity or magnetism. It gets stronger. The energy needed to separate them grows and grows until, poof, there's enough energy in the bond to create a brand new pair of quarks out of thin air. You don't end up with a free quark. You end up with two new pairs. This is called color confinement, and it means that in our normal universe, you can never find a quark or a gluon by itself. They are forever locked away inside protons and neutrons. But what if you could bust them out? What if you could heat matter to such an insane temperature that the protons and neutrons themselves just melt? This is the question that drove physicists to build some of the most powerful machines on Earth. Particle colliders like the Relativistic Heavy Ion Collider, RHIC, in New York, and the Large Hadron Collider, LHC, in Switzerland. The concept is basically one of overwhelming force. These machines take heavy atoms, like gold or lead, and accelerate them in opposite directions to over 99.9% the speed of light. Then, they're smashed into a head-on collision. The energy released in this tiny, subatomic crash is monumental. For a fleeting moment, less than a trillionth of a second, the conditions are the same as they were in the first microseconds of the universe. In this unimaginable fireball, protons and neutrons are obliterated. The quarks and gluons are set free. They roam in a hot, dense, seething soup, the quark-gluon plasma, or QGP. Studying it is like cosmic archaeology. We're looking at the fossilized state of the infant universe. When physicists first started making QGP in the early 2000s, they thought they knew what they'd see. They expected a plasma, in the traditional sense, behaving like a gas of free-flying particles. But when the data came in, it showed something completely different. Something astonishing. The quark-gluon plasma did not behave like a gas at all. It behaved like an almost perfect liquid. It flows with virtually zero internal friction, making it the most perfect fluid ever observed. Its flow isn't random, like particles in a gas, it's collective and coordinated. One piece of evidence came from the shape of the explosions. Sometimes the colliding atoms create a football-shaped fireball. The pressure then causes more particles to fly out along the short axis than the long one. This coordinated flow is a classic sign of a liquid, not a gas. Another clue comes from jet quenching. When two particles collide, they often produce a pair of high-energy quarks that fly off in opposite directions, creating two jets of particles. But inside the QGP, if one of those quarks has to travel through the dense, soupy plasma, it loses energy and its jet gets quenched, like a bullet fired into water. The other jet, closer to the edge, escapes just fine. This shows just how dense and interactive the QGP is. So the primordial soup of creation, the very first state of matter, turns out to be a liquid. A frictionless, super-hot liquid that existed for only a few millionths of a second after the Big Bang. This discovery was a profound revelation, forcing scientists to rethink the nature of the strong force. By smashing atoms together, we are, for the briefest moment, holding a drop of the Big Bang in our hands, studying the very substance from which everything we know eventually came. Conclusion: we started this journey in the comfortable, everyday world of solids, liquids, and gases. We have since traveled to the absolute edges of physical reality, to places where those rules are not just bent, but shattered. We plunged into absolute zero and found superfluids, ghostly liquids that flow without friction and defy gravity. We pushed even colder and found the Bose-Einstein condensate, where thousands of atoms become one massive, superatom, that can capture light itself. And then we rocketed to the other extreme, into a trillion-degree inferno, and witnessed the quark-gluon plasma. Not a gas, but a perfect liquid that filled the universe in its first moments. So what does this all tell us? It reveals a hidden truth about our universe. The neat, classical world we see every day is just an illusion of scale. It's a facade. Underneath it all, at the extremes of temperature and energy, a much weirder, collective quantum reality takes over. The lines between individual particles blur and dissolve. Matter stops being a bunch of tiny, separate things and starts behaving like a single, unified, and deeply strange entity. These discoveries are more than just party tricks for physicists. They're unlocking the future. The quantum control we have with BECs is paving the way for quantum computers and ultra-precise sensors. Superfluids are essential for tech like MRIs and could one day help us detect the particles of gravity itself. And by recreating the quark-gluon plasma, we are learning how the universe itself was born. Solid, liquid, and gas are not the end of the story. They're just the first chapter in a cosmic rulebook we're only now beginning to read. These impossible materials show us that reality is more fluid, more connected, and infinitely more mysterious than we ever thought possible. They remind us that the goal of science isn't to have all the answers, but to keep exploring a universe that will never run out of ways to astonish us. If your mind is just a little bit blown right now, make sure to hit that subscribe button and ring the bell so you never miss another exploration into the unknown. What other bizarre states of matter have you heard of, or what mysteries of the cosmos would you like us to tackle next? Let us know in the comments below. And if you want to support our journey into the deepest questions of science, consider sharing this video with a friend who is ready to have their reality challenged. The universe has a density limit and we're getting close. In some places, the universe is almost perfectly empty. A cold, expanding void so vast that our entire galaxy would be a lonely speck within it. The space between things stretches for hundreds of millions of light years, a quiet darkness where, on average, you'd find only a handful of atoms in a space the size of a room. In other places, it is impossibly full. In the core of a collapsed star, a single thimbleful of material has the mass of a mountain, compressed to a point that tests the very laws of physics. This is a journey through those two extremes. Not science fiction, but the real architecture of our cosmos, shaped by deep time, fundamental forces, and the nature of matter itself. It's a story that begins within an invisible web that organized the universe from the very beginning, and it ends at the absolute breaking point of reality. All of it stretches our idea of what the universe can be. The great emptiness. When we look into the night sky, it appears full of things. A field of stars, the soft glow of our own galaxy, a faint, distant spiral. It gives the impression that we are surrounded by cosmic stuff. But this perspective is an illusion, a result of our particular place in it all. In truth, we are in an ocean of emptiness, and the lights we see are just the rarest crests on its waves. The vast majority of the universe's volume is composed of enormous regions of near-total vacuum known as cosmic voids. These aren't just the quiet spaces between stars. They are chasms of non-existence on a scale that is difficult to comprehend. The most well-known of these is the Boötes void. It's a colossal, nearly spherical region of space with a diameter estimated to be around 330 million light-years. To put that in perspective, if our Milky Way galaxy were at its center, our closest galactic neighbor, Andromeda, would be just a tiny step away in our own cosmic backyard. We simply wouldn't see the light from the edge of the void for another 165 million years. Based on the average density of matter in the cosmos, astronomers would expect to find thousands of galaxies in a volume this large. The Boötes void, however, appears to contain only about 60. It's an absence so profound it feels like a mistake in the cosmic blueprint. And it's not unique. Our own galaxy resides in a much smaller, but still significant void called the local hole. For a long time, as astronomers mapped the universe in greater detail, a picture emerged. It wasn't one of evenly scattered galaxies, but something that resembled foam or a sponge. The bright filaments of galaxies are the walls of this foam, and the voids are the giant, expanding bubbles in between. These voids are the dominant feature of the universe's large-scale structure. But how did this happen? If the universe began in a hot, dense state, shouldn't everything be spread out more or less evenly? Why would gravity, a force that pulls things together, result in a cosmos defined by its emptiness? The answer, we think, lies in the moments just after the Big Bang. The early universe was incredibly smooth, but not perfectly so. There were tiny, random quantum fluctuations, ripples in the primordial soup. Some regions were infinitesimally denser than others. These were the seeds of all future structure. As the universe expanded, gravity began its slow, patient work. The regions that were even slightly denser started to pull in more matter, growing over time. The regions that were slightly less dense began to lose what little matter they had to their neighbors, becoming emptier. It was a gradual feedback loop. The underdense regions expanded and merged, creating the vast cosmic voids we see today. The denser regions, meanwhile, were pulled together into long, thin strands. This process shows us a fundamental truth. The structures and the voids are two sides of the same coin. The emptiness is a necessary consequence of creating structure. To build the brilliant clusters of galaxies, the universe had to excavate the material from somewhere else. The universe is not just the things in it, it is also the space between those things. And to get to the densest places in the cosmos, we have to follow the map that connects everything, the cosmic web. Riding the cosmic web, the cosmic voids are not just empty holes. They are defined by what surrounds them. When astronomers create large-scale maps of the universe, they reveal a truly breathtaking structure. A network of impossibly long, delicate filaments made of galaxies, stretching across billions of light years. This is the cosmic web. From a distance, it looks almost organic, like luminous thread or the neurons of a colossal brain. Each point of light is an entire galaxy. Where these filaments meet, they form dense knots, galaxy clusters, the great cities of the cosmos, where thousands of galaxies are bound together by gravity. This entire visible structure, however, is built on an invisible scaffold. The architect of the cosmic web is not the ordinary matter we can see, but the mysterious substance we call dark matter. Dark matter makes up about 27% of the universe's mass and energy content. It doesn't interact with light, so we can't see it, but it does exert a gravitational pull. There's about 5 times more dark matter than the regular, baryonic matter that makes up you, me, and the stars. And according to our leading cosmological model, it was the dark matter that collapsed first. Structure in the universe grew from the bottom up. Small clumps of dark matter were the first to collapse under their own gravity. Over cosmic time, these small halos merged to form larger and larger ones. Because dark matter was so much more abundant, its gravity created the cosmic framework first, an invisible network of filaments and clusters, creating deep gravitational wells. The ordinary matter, the gas and dust we see, simply fell into this pre-existing structure. Like water flowing into the low points of a landscape, it was funneled by gravity along the dark matter filaments, pooling in the deepest wells at the intersections. It was there, in those dense reservoirs, that the first stars and galaxies ignited. So, when we see a filament of galaxies, what we're really seeing is the visible matter that has settled onto an underlying, much larger structure of dark matter. The galaxies are like streetlights illuminating the invisible cosmic highways. Powerful instruments like the James Webb Space Telescope have allowed us to map this underlying scaffold in more detail than ever before, confirming how its structure gives rise to both the busiest and loneliest places in the universe. To journey from a void to a place of extreme density is to travel along one of these filaments. As you move from the profound emptiness, you would begin to see more galaxies, first small and scattered, then arranged in a distinct line, a river of stars. You are now riding the cosmic web. Traveling along this filament is a journey of increasing density. Gravity is always at work, pulling galaxies toward the great intersections. You would see them collide and merge, triggering bursts of new star formation. Invisible streams of hot gas flow along these cosmic rivers, feeding the galactic clusters at the nodes. It's a dynamic, evolving ecosystem. Our journey continues deeper into the filament toward a massive galaxy cluster. And within one of these galaxies, an enormous star is nearing the end of its life. For millions of years, it has been fighting a battle against its own gravity. It is a battle it's about to lose, in a cataclysm that will forge the next stage of our journey. An object so dense, it represents matter at its breaking point. The breaking point of matter. For millions of years, the massive star was a stable furnace. In its core, immense pressure and heat fused lighter elements into heavier ones, releasing energy. This outward radiation pressure perfectly balanced the inward crush of gravity. This process has a natural endpoint: iron. Fusing iron doesn't release energy, it consumes it. With its fuel source gone, the outward pressure vanishes. In less than a second, the star's core, with a mass greater than our Sun, collapses inward. The outer layers free fall toward the center at nearly a quarter of the speed of light. This implosion rebounds, sending a shockwave hurtling back out through the falling material. The result is a Type II supernova, an explosion that can briefly outshine its entire galaxy. The outer layers are cast out into space, seeding the cosmos with heavy elements. But what remains of the core? If it's massive enough, it forms a black hole. But if its mass is below a certain threshold, the collapse is stopped by a purely quantum mechanical force. What's left is a neutron star. To understand a neutron star is to confront a state of matter that is difficult to imagine. As the core collapses, the density becomes so great that the structure of atoms is destroyed. Gravity overcomes the electromagnetic force, and electrons are forced into protons, combining to form neutrons. This process, called inverse beta decay, transforms the entire core into a city-sized sphere made almost entirely of neutrons, packed as tightly as they are in an atomic nucleus. It is a truly unique object. A single teaspoon of this material would weigh billions of tons. But what holds it up? Why doesn't it keep collapsing? The answer is a quantum rule called the Pauli exclusion principle. It states that two identical particles of a certain class, like neutrons, cannot occupy the same quantum state in the same place at the same time. In a smaller star's remnant, a white dwarf, this principle applies to electrons, creating electron degeneracy pressure. But in the formation of a neutron star, gravity is strong enough to overcome that. The collapse continues until the asterisk neutrons themselves are pushed shoulder to shoulder. At this point, neutron degeneracy pressure kicks in, a powerful repulsive force that finally halts the collapse. This state of matter is not quite solid, liquid, or gas. Some theories suggest its core is a superfluid of neutrons that flows with zero friction. But even this incredible force has a limit. There is a maximum mass that neutron degeneracy pressure can support before it, too, is overwhelmed. This is known as the Tolman-Oppenheimer-Volkoff, or TOV, limit. The precise value of the TOV limit is still a subject of careful research. Current observations, including the landmark detection of gravitational waves from merging neutron stars, have helped constrain this limit to around 2.2 times the mass of our Sun for a non-rotating star. And astronomers have found candidates that push right up against this boundary, with measured masses as high as 2.35 solar masses, testing our understanding of how dense matter can possibly get before it must collapse. If a star's core is more massive than the TOV limit, or if a neutron star gains enough mass from a companion, nothing can stop the final collapse. Gravity becomes supreme. The star crushes itself down to a point of infinite density, a singularity, and becomes a black hole. This is the ultimate limit. A neutron star represents matter at the absolute brink. Any denser, and it disappears from the observable universe. But could there be one more step? It's possible that under the even more extreme pressure inside the most massive neutron stars, the neutrons themselves might dissolve into their constituent particles, known as quarks. This would create a quark star, an even denser and smaller object. Proving their existence is one of the great quests of modern astrophysics. They may be the last stable stop on the line before matter gives up and collapses forever. Conclusion: our journey has taken us across the universe, from one extreme of density to the other. We began in the staggering emptiness of a cosmic void, where the universe is defined by its absences. We learned that this emptiness was not a flaw, but a feature, the material excavated by gravity to build something else. Then, we rode the cosmic web, the glowing network built on an invisible scaffold of dark matter, and saw how gravity funnels matter along cosmic rivers, creating a universe that is both intricately structured and profoundly empty. Finally, we arrived at the breaking point. In the heart of a dead star, we found matter crushed so densely that the familiar laws of chemistry no longer apply. We found the neutron star, a city-sized atomic nucleus held up by the strange rules of the quantum world, and we found its limit, a final boundary beyond which matter can no longer exist as we know it. The universe is a story of this tension, the outward push of expansion making the voids larger, and the inward pull of gravity sculpting matter into ever denser forms. From the ghostly voids to the cores of dead stars, we see a cosmos built upon this dichotomy. We live in the in-between. The carbon in our bodies and the iron in our blood were forged in the hearts of stars and scattered by the very explosions that create these dense remnants. We are born from the ashes of cosmic density, living on a small, rocky island in a vast ocean of near-nothingness. Our existence is a quiet reminder that the universe, through all its extremes, finds a way to build complexity. We are the improbable children of both the void and the limit. If this calm exploration into the cosmos has sparked your curiosity, consider subscribing and turning on notifications. We have many more journeys to take together. Scientists just filmed an impossible state of matter. You think you know how ice melts? Well, you probably don't. We all learn it in school. You add heat to a solid, its atoms vibrate, break their bonds, and the rigid, orderly structure collapses into the jumbled mess of a liquid. It seems like a simple, one-way street. A sharp transition that happens in the blink of an eye. For decades, we've believed this was a fundamental rule of the physical world. Solid to liquid, order to disorder. It's clean, predictable, and it's what happens every time you leave an ice cube out on the counter. But what if it's not? What if that's just a convenient story we've been telling ourselves because we could never see what was really going on? Well, scientists just used a powerful, atomic-scale camera to film the process of melting for the first time. And they discovered a secret, impossible, phase of matter hiding in plain sight. What they found challenges what we thought we knew about physics, and it all starts with a single layer of atoms that behaves in a way we never thought possible. They found a state that is neither solid nor liquid. A ghostly, in-between, phase that shouldn't exist, where atoms are caught in a bizarre dance between two worlds. This isn't just some weird exception. It's a discovery that forces us to reconsider the simple models in our old textbooks about the very nature of matter itself. The world at the atomic scale is far stranger and more complex than we ever imagined. And for the first time, we have the footage to prove it. The world we thought we knew, the dogma of melting. Before we can really appreciate how big of a deal this is, we need to go back and understand the world as physics saw it just a few months ago. We need to understand the old reality. For over a century, the story of matter had three main characters: the solid, the liquid, and the gas. Imagine a grand ballroom. In a solid, atoms are like dancers in a perfectly choreographed waltz, arranged in a repeating, crystalline lattice. Every atom knows its precise place. It can jiggle with energy, but it can't leave its spot. This is a world of supreme order. The bonds between them are strong, like the unyielding grip of the dancer's hands. This structure is what makes a solid, solid, giving it a fixed shape and hardness. Think of a diamond, where carbon atoms are locked in a near-perfect grid. Now, let's turn up the heat. In our ballroom, this is like swapping the waltz for a chaotic rock anthem. The dancers gain energy, vibrating more and more violently until, snap. The bonds holding them in place break. This is the melting point. And it's not a gentle process, it's a catastrophic failure of the whole system. In three-dimensional materials, the kind we see every day, this is what physicists call a first-order phase transition. It's abrupt, it's total, and it happens at a single, precise temperature. At 0 degrees Celsius, you have ice. At 0.0001 degrees, you have water. There is no in-between. Once melted, our dancers are in a mosh pit. This is the liquid state. The atoms are a disordered, chaotic jumble. They have no fixed positions and are free to slide past one another, which is why a liquid flows to fill whatever container it's in. The elegant waltz has devolved into a frenzy. There's still some attraction between the atoms. That's why water forms droplets. But the rigid, long-range order of the solid is completely gone. And if we keep adding heat, the dancers are flung apart entirely, each one flying off into the far corners of the room. That's the gas phase, a world of near-total chaos. This solid-liquid-gas model is the bedrock of classical thermodynamics. It's a beautifully simple framework that explains everything from steam engines to refrigerators. It was built by giants of 19th-century physics who established the mathematical laws of phase transitions, and for them, the sharpness of the melting point was a law carved in stone. Our entire technological world is built on this model. Engineers rely on the predictable, solid state of steel to design bridges, and chemists rely on the properties of liquids as solvents. The idea that melting is a binary switch, on or off, solid or liquid, is baked into our fundamental understanding of reality. But science is a story of ever-increasing resolution. We build better tools, we look closer, and the simple truths we held dear are often revealed to be just approximations of a much more fascinating reality. And as we're about to see, cracks in this perfect model were already showing long before this new discovery. The universe, it turns out, has secrets hidden in the spaces between the states we thought we knew. Cracks in the foundation, the weirdness on the edge. Of course, the idea that matter only comes in three simple flavors was always an oversimplification. Physicists have known for a while that nature has a much stranger imagination. Take liquid crystals, the tech behind the screen you might be watching this on. A liquid crystal is a bizarre hybrid. Its molecules can flow like a liquid, but they all tend to stay pointed in the same direction, retaining a bit of solid-like order. It's a state that defied the simple trinity of solid, liquid, and gas and sparked a technological revolution. Or what about glass? It looks solid. It's rigid and hard. But at the atomic level, it's chaos. The atoms are frozen in a completely random arrangement, just like a liquid. A glass is essentially a liquid that got stuck before it had a chance to organize itself into a proper crystal. And at the extremes, things get even weirder. Cool atoms to a fraction of a degree above absolute zero, and you can create a Bose-Einstein condensate, where millions of individual atoms lose their identity and act as a single, superatom. These exotic states were fascinating, but they were often seen as special cases. For a simple, everyday crystal, the rule was still the rule. Melting was a sharp, first-order transition from order to chaos. But the real trouble started on the frontier, the world of two dimensions. The 2016 Nobel Prize in Physics celebrated the bizarre properties of 2D materials like graphene, which are just a single atom thick. In a 3D world, Atoms are locked in by neighbors above, below, and on all sides. But when you strip away that third dimension, all hell breaks loose. The rules change. The random jiggling of atoms has a much more dramatic effect. Back in the 1970s, a group of theoretical physicists, Kosterlitz, Thouless, Halperin, Nelson, and Young, developed what became known as the KTHNY theory. They made a startling prediction. In 2 dimensions, melting shouldn't happen all at once. It couldn't be a simple, abrupt jump. Instead, they argued that a 2D crystal should melt in a 2-step process, giving birth to a completely new, intermediate phase of matter they called the hexatic phase. For decades, this was a beautiful but unproven theory. It was glimpsed in computer simulations and in models using large particles, but never in a real, atomically thin crystal. Was the hexatic phase a mathematical curiosity, or was it a real, physical state of matter? To find out, scientists would need to build a camera that could film individual atoms as they dance on the edge of existence. They would need a laboratory the size of a pinhead. The stage was set for one of the most challenging experiments in materials science history. The breakthrough, filming the impossible. For decades, watching a single atom was science fiction. The wavelength of visible light is thousands of times larger than an atom, so seeing one with a normal microscope is like trying to feel the bumps on a record with a beach ball. To see atoms, you need something with a much smaller wavelength. You need electrons. This is the principle behind the transmission electron microscope, or TEM. It's a massive piece of equipment, often over 10 feet tall, that fires a high-energy beam of electrons through an incredibly thin slice of material. Magnetic lenses then focus these electrons to form an image with such high resolution that you can see individual atoms. But filming atoms as they move and rearrange during a process like melting is a monumental challenge. First, your sample has to be almost unimaginably thin, just a single atom thick. Second, the electron beam itself is destructive. It's like trying to watch a delicate snowflake melt by hitting it with a stream of microscopic bullets. And you have to do all of this while heating the sample with extreme precision inside the microscope's vacuum. This is exactly the challenge an international research team, led by scientists at the University of Vienna, took on in a landmark 2026 study. Their goal? To finally film a 2D crystal as it melted and prove the hexatic phase was real. They started with a material called silver iodide, silver 1 iodide. It has a hexagonal crystal structure, much like ice, and it can form stable, single-atom thick layers. This structural similarity is why it's famously used for cloud seeding to create rain. The next problem was protecting this delicate layer while they blasted it with electrons and heated it up. Their solution was a stroke of nano-engineering genius. They created the world's thinnest sandwich. They placed the single atomic layer of silver iodide between 2 sheets of graphene. Graphene, the Nobel-winning wonder material, is not only incredibly strong but also transparent to the electron beam. This graphene sandwich acted as a perfect, protective viewing chamber. They placed their nano sandwich inside an advanced STEM microscope, slowly cranked up the heat past 1100 degrees Celsius, and started rolling the camera. The sheer amount of data was staggering, thousands of high-resolution images capturing the atomic chaos. Analyzing it by hand was impossible. As senior author Kimmo Mustonen explained, without the use of AI tools such as neural networks, it would have been impossible to track all these individual atoms. So, they trained an AI to go through every frame, identify every atom, and track its movement. As the temperature rose, they watched the solid crystal. The atoms were locked in their perfect hexagonal lattice. But as the melting point approached, something incredible happened. The crystal didn't just collapse. Instead, the atoms began to lose their fixed positions and slide past one another. The rigid, long-range positional order of the solid was gone. It looked like a liquid. But a ghost of the old order remained. While the atoms were no longer in a perfect grid, they still tried to maintain their original hexagonal arrangement with their immediate neighbors. The orientational order was still there. Imagine our ballroom dancers again. They're no longer in fixed spots, they're all over the floor. But each dancer is still trying to hold their arms out to form a hexagon with their 6 closest neighbors. The large-scale structure is gone, but the local formation persists. This was it. This was the hexatic phase, caught on camera for the first time in a real material. A state that's partially solid and partially liquid. It wasn't just a fleeting moment. It existed in a stable window of about 25 degrees Celsius below the final melting point. The 50-year-old prediction of KTHNY theory was finally, stunningly confirmed. The scientists had filmed the impossible. But in doing so, they also found something that would turn the theory on its head. The new reality, rewriting the laws of melting. The discovery of the hexatic phase was a huge win for a half-century-old theory. The KTHNY theory had correctly predicted that 2D melting would be a two-step dance. First, the crystal loses its positional order to become hexatic. Then, it loses its remaining orientational order to become a liquid. But KTHNY theory made another crucial prediction. It claimed that both of these transitions should be continuous, or second-order, phase transitions. A continuous transition is a gradual, smooth process, like slowly turning up a dimmer switch. The theory said the solid should smoothly morph into the hexatic phase, which would then smoothly morph into the liquid. As the Vienna team analyzed their atomic scale movie, they saw the first part play out perfectly. The transition from solid to hexatic was indeed a smooth, continuous process. It was a perfect match. But then came the shock. When they heated the material further, to go from the newfound hexatic phase to the final liquid state, the transition wasn't smooth at all. It was abrupt, catastrophic. It was a first-order transition, the same kind of sudden jump we see when 3D ice melts into water. The ghostly orientational order didn't just fade away, it shattered. At a specific temperature, the whole system suddenly collapsed into the complete disorder of a liquid. This single observation broke the theory. The elegant KTHNY model, which had brilliantly predicted the hexatic phase's existence, was wrong about how it died. Melting in 2 dimensions was a hybrid process, a smooth, continuous transition into a secret intermediate state, followed by a violent, abrupt collapse into a liquid. A major physics theory had been confirmed and broken in the very same experiment. So, what does this all mean? On a fundamental level, it forces physicists to develop a new, more complete theory of phase transitions that can account for this weird hybrid behavior. But the practical implications are even more exciting. Modern electronics are all about engineering materials atom by atom. This discovery gives us a completely new tool. By understanding that states like the hexatic phase exist, we can start to design materials that use their unique properties. Imagine a flexible phone with circuits made from a 2D material. If it melts via a hexatic phase, it could become soft and pliable without completely failing. This could pave the way for truly resilient, bendable electronics or even sensors integrated directly with human tissue. This new science could also revolutionize catalysis, the process of speeding up chemical reactions. The unique, semi-ordered state of a hexatic material could offer novel catalytic properties that neither a perfect solid nor a chaotic liquid can. We're moving beyond just solid, liquid, and gas and into an era of designer matter, where we can create materials with custom properties by nudging them into these strange, in-between states. This journey, from a simple picture of melting to a complex atomic dance, is what makes science so endlessly fascinating. Every time we look closer, the universe reveals another layer of complexity. If you want to keep exploring these mind-bending discoveries that are rewriting our understanding of reality, make sure to subscribe. The universe is full of secrets, and we're here to uncover them together. Conclusion. So, the next time you watch an ice cube melt, remember what you've seen today. Remember that beneath that everyday phenomenon lies a hidden world of unimaginable complexity. We started with a simple rule: solids melt into liquids. It was a story of black and white. But by building a camera powerful enough to see the atoms themselves, we've discovered the truth is written in shades of gray. Scientists at the University of Vienna, with their graphene sandwich and AI copilot, filmed a ghost. They captured the hexatic phase, a state of matter caught between the perfect order of a solid and the chaos of a liquid. In doing so, they proved a 50-year-old theory right and wrong at the same time. They showed us that nature is more subtle and ingenious than our theories often give it credit for. This isn't just a new page in a textbook. It's a doorway to a new era of technology where we can design materials that live in this twilight world, creating flexible electronics that don't break and hypersensitive sensors. The discovery of the hexatic phase is a profound reminder that what we perceive is limited only by our tools to observe it. For centuries, melting was a simple switch because we could only see the before and after. Now, we can finally see the during. We can watch the dance. And it has changed everything. We are peeling back the layers of reality, one atom at a time. And we're finding that at the fundamental edge of existence, the rigid rules of our world dissolve into a fluid, probabilistic, and utterly beautiful quantum ballet. The journey into the heart of matter has just begun. Reality's ultimate ingredient has no form. Everything you can see, your hands, the stars, the device you are watching this on, seems solid and real. It feels like it is made of things. And yet, all of it grows from an ingredient that has no form, no substance, and no solidity of its own. 2,500 years ago, a few thinkers in the ancient world proposed a strange idea: that all of reality springs from a pure, formless potential. It was an idea that seemed to belong more to abstract thought than to the real world, and for a long time, it was set aside. But what those early thinkers could not have known is that our own modern science would eventually circle back and find that strange idea waiting. This is a journey into that idea. Not as a myth, but as a concept that has quietly woven its way through the history of how we see the world. If this kind of calm exploration into the nature of reality is something you enjoy, consider liking the video and subscribing to the channel. And wherever you are right now, whether it's morning or night, or somewhere in between, feel free to share where you're watching or listening from. What is the world made of? It is, perhaps, one of the oldest questions we have. From the moment our distant ancestors looked at the world with a curious mind, they must have wondered: is the rock in my hand ultimately made of the same stuff as the water in the river, or the light from the sun? For millennia, this quiet question has guided our greatest thinkers. The story of this question is often told as a straight line, a journey from blurry, philosophical pictures to a sharp, scientific one. We imagine ourselves moving from simple ideas, like earth, air, fire, and water, to a world made of tiny, solid atoms. And from there, to even smaller particles inside them. It seems like a clear path of discovery. But what if that story isn't quite right? What if the journey was not a line, but a circle? What if one of the most ancient, most abstract ideas about reality turned out to be a surprisingly accurate description of the world our best science has revealed? This is the story of a concept that for centuries seemed to have no place in a rational, scientific world. The idea that the fundamental ingredient of all existence isn't a asterisk thing at all. It is pure, undefined, formless potential. It's an idea that was set aside by the forward march of science, only to reappear in the strange and beautiful world of 21st century physics. We are going to journey from the minds of ancient philosophers to the heart of our most powerful scientific instruments, and we will discover how science is now meeting a quiet, fundamental truth: that reality's ultimate ingredient has no form. To begin our journey, we have to travel back in time. Back to the shores of Ionia in the 6th century BCE, in what is now modern-day Turkey. Here, a new way of thinking was taking hold. For the first time, people were trying to explain the world not just through myths, but through observation and reason. They were the first philosophers, and they were gently obsessed with that one question: what is everything made of? The first of these thinkers we remember is Thales. He looked at the world and saw water everywhere. Water is essential for life. It can be a liquid, a solid, or a gas. His conclusion was simple and logical. Everything, at its core, must be water. A later thinker, Anaximenes, disagreed. He argued the fundamental substance must be air. Air, he reasoned, could thin out to become fire, or condense to become wind, then water, then earth, and stone. Each was a careful attempt to find a single, underlying substance. But it was another philosopher from Miletus, Anaximander, who proposed something quietly different. He looked at the ideas of his peers and saw a simple problem. If everything is made of water, how can its opposite, fire, exist? If the foundation of reality had any single quality, if it were wet, or dry, or hot, or cold, it could never give rise to its own opposite. His solution was a remarkable step into abstract thought. He reasoned that the source of all things, the first principle, could not be any of the elements we see around us. It had to be something more fundamental, something without any of the properties of the things it creates. He called it the apeiron. In Greek, apeiron means unlimited, boundless, or indefinite. It was a substance that was no thing. It had no specific qualities of its own. It wasn't hot or cold, wet or dry. It was an eternal, indestructible source from which everything emerges, and to which everything eventually returns. In Anaximander's view, the world of opposites we see, hot and cold, light and dark, arises from this formless potential, exists for a time, and then dissolves back into it. Think about how unusual this idea was for its time. Other thinkers were pointing to things you could see and touch. Anaximander was pointing to a concept. He was arguing that the foundation of all physical reality was something that was, itself, not physical in any recognizable sense. It was pure potential. It's not surprising that this idea was difficult to grasp, and was soon overshadowed by more tangible theories, like the four elements, or the atoms of Democritus. But the idea did not disappear. 2 centuries later, it was refined by perhaps the most systematic philosopher of all, Aristotle. Aristotle wanted to understand not just what things were, but how they change. How does an acorn become an oak tree? How does a block of marble become a statue? His analysis led him to a quiet and profound conclusion. Every physical thing, he argued, is a combination of two principles: matter, (hyle asterisk), and form, (morphe). Form, for Aristotle, is not just shape. It is a thing's entire set of qualities, its structure, its function, what makes it what it is. The form of a statue is its shape and the figure it represents. The form of an oak tree is its oakness, its structure of roots, trunk, and leaves, and its purpose of growing and reproducing. Form is what makes something the specific thing that it is. Matter, on the other hand, is the underlying stuff that receives the form. For the statue, bronze or marble is its matter. For the oak tree, the wood and tissues are its matter. Change happens when the same matter loses one form and takes on another. But Aristotle followed this logic to its absolute limit. He asked, what is the matter of the bronze, or the wood? You can break things down. A tree is made of tissues, which are made of cells, which are made of molecules. The molecules are made of what Aristotle's time believed were the elements: earth, water, air, and fire. But what is the matter of the elements themselves? If one element can change into another, there must be some underlying stuff that is common to both. This led Aristotle to the concept of prime matter, prot hyle. Prime matter is the ultimate foundation of all physical reality. And just like Anaximanders of Piran, it has absolutely no form of its own. It is pure potential. It is not a thing. You can never see it or touch it. Because the moment you could perceive it, it would have some quality, some color, some texture. And therefore it wouldn't be prime matter anymore. It only ever exists together with a form. It is the absolute potential to become anything, while itself being nothing in particular. For centuries, this was a central idea in philosophy. But to the emerging scientific mind, it sounded like abstract nonsense. How can something exist that has no properties? Science deals with what is measurable and observable. And so, as a new era of science began, the idea of a formless ingredient was quietly left behind, replaced by a much simpler and more intuitive picture of the world. A world made of tiny, solid, definite things. The scientific view that grew from the 17th century onward was one of reassuring certainty. It was a clockwork universe, operating according to fixed and knowable laws, as imagined by Isaac Newton. The fundamental stuff of this universe was not some vague potential, but solid, indestructible matter. This idea had its own roots in ancient Greece, with the atomists, who suggested everything was made of tiny, indivisible particles called atoms moving in a void. For them, the atoms themselves were the fundamental reality. They had definite properties, like size and shape. All the variety in the world was just a different arrangement of these eternal atoms. This atomic theory was reborn with the scientific revolution. It was simple, elegant, and it worked. It helped explain chemistry, mechanics, and the properties of gases. The world was a grand collection of tiny billiard balls. Reality was fundamentally solid and knowable. The philosophical idea of a formless matter had been replaced by the clear, rational light of mechanical science. For 200 years, this model was incredibly successful. It gave us a complete and satisfying picture of the cosmos. The world was made of things. Hard, definite, predictable things. But then, at the very end of the 19th century, as scientists began to look deeper into this solid matter, the clockwork picture began to show quiet cracks. The first was the discovery of the electron in 1897. The atom, whose name meant uncuttable, was in fact cuttable. It had parts. Then came the discovery of radioactivity. Atoms weren't eternal and unchanging after all. They could spontaneously transform from one element into another. This was a quiet challenge to the clockwork model. The fundamental building blocks of reality weren't entirely stable, they could change. It was as if matter was shedding one form and taking on another. But the old way of thinking in terms of things remained. The electron was just a smaller thing. But the really deep challenge to the world of solid forms came not from breaking matter down, but from energizing it. This brings us to the first piece of modern evidence for a world beyond simple forms. The fourth state of matter, plasma. We learn in school about solids, liquids, and gases. You take a solid, like ice, add energy, and it melts into liquid water. Add more energy, and it boils into a gas. In each step, the H2O molecules are still H2O molecules. Their basic form remains. But what happens if you keep adding energy? What if you heat a gas to thousands or millions of degrees? At a certain point, the energy becomes so intense that it rips the electrons away from their atomic nuclei. The neat, orderly structure of the atom is gone. What you're left with is no longer a gas of neutral atoms, but a chaotic soup of free-floating electrons and positively charged ions. This is plasma. While we call it the fourth state of matter, it is fundamentally different. In a plasma, matter loses its familiar atomic form. The definition of an element like helium, a specific number of protons with matching electrons, dissolves. It's just a roiling swarm of charged particles. We don't see much plasma in our cool, low-energy lives on Earth. But in the wider cosmos, plasma is not the exception, it is the rule. An estimated 99% of the visible matter in the universe is in the plasma state. Every star, including our Sun, is a giant ball of plasma. The vast spaces between galaxies are filled with a thin plasma. Lightning is a brief filament of plasma, as air is torn apart. Plasma is our first physical glimpse of matter where its familiar structure has dissolved back into a more primitive, chaotic state. It demonstrates a quiet but crucial principle: form is not fundamental. It is a property that matter can take on, or lose, depending on its energy. The classical world of solid, unchanging atoms was a low-energy illusion, a special case that exists in the calm corners of the universe, like our own planet. The discovery of plasma showed that the supposedly solid nature of matter was fragile. Underneath the appearance of stable forms lay a more fundamental and chaotic reality. It was a powerful hint that the ancient philosophers were onto something. But this was only the beginning. The cracks that plasma opened were about to widen, with a revolution that would ask us to question what particle and reality even mean. This was the quantum revolution. The world of plasma showed us that the familiar forms of atoms are not permanent. But even in a plasma, we still think in terms of things. We pictured tiny electrons and ions zipping around. It's still a collection of very small objects, just moving chaotically. The quantum revolution, however, would ask us to let go of this final intuition. The idea that reality is made of particles at all. The journey into the quantum realm began in the early 20th century, and it revealed a world that did not follow familiar rules. Light, long understood as a wave, was found to sometimes behave like a particle, a photon. Electrons, thought to be definite particles, were found to behave like waves. A single electron could seemingly pass through two slits at once, as if it were smeared out. This wave-particle duality was the first sign that our basic picture of reality was incomplete. Then, Werner Heisenberg's uncertainty principle showed that you could never know both the precise position and the precise momentum of a particle at the same time. The more you knew about one, the less you knew about the other. It wasn't a limit of our tools. It was a fundamental feature of reality itself. A quantum particle was not a tiny, solid point, but a strange cloud of possibilities. As Heisenberg himself suggested, there was a quiet echo of Aristotle here. The quantum state of a particle, before it is measured, is not yet actual. It exists in a state of potentiality, a range of possibilities. The act of measurement gently coaxes one of those possibilities into becoming real. For some physicists like Heisenberg, Aristotle's philosophy became a useful analogy for this new, strange reality. This was already hard to grasp. But the truly deep shift in our understanding came with quantum field theory or QFT. Developed over decades by minds like Paul Dirac and Richard Feynman, QFT is the language of all modern particle physics. It is perhaps the most successful scientific theory we have ever created. And its central message is this: the most fundamental building blocks of the universe are not particles. They are fields. We are familiar with fields from magnets. A magnetic field is an invisible influence that fills the space around a magnet. You can't see the field, only its effects. Quantum field theory asks us to imagine that the entire universe is completely filled with a collection of these fundamental, fluid-like substances, the quantum fields. There is an electron field that permeates every corner of the cosmos. There is a photon field for electromagnetism. There are quark fields, a Higgs field, and so on, a field for every particle we know. In their resting state, these fields are invisible, dormant, and formless. They are the quiet baseline of reality. So where do particles come from? This is the beautiful insight of QFT. A particle is nothing more than a localized vibration, or an excitation, in its field. The best analogy is a vast, perfectly calm ocean that stretches to infinity. This ocean represents a quantum field in its quietest state. It's just there, a formless potential. Now, imagine you tap the surface of the ocean. A ripple spreads out. That ripple, that localized, temporary disturbance, is what we call a particle. An electron is not a tiny object moving through space. An electron is a ripple in the electron field. A photon of light is a ripple in the electromagnetic field. The particle is not the fundamental thing. The field is the underlying, continuous reality. The particle is just a brief pattern appearing on it. Suddenly, the strangeness of quantum mechanics begins to make a different kind of sense. Wave-particle duality? A ripple in a field naturally has both wave-like properties and particle-like properties. The uncertainty principle? It makes sense that a ripple wouldn't have a perfectly defined position and momentum at the same time. QFT also explains how particles can be created and destroyed. When particles collide at high energies, that energy is dumped into the various quantum fields at the point of impact. This causes the fields to vibrate, and new ripples, new particles, are created, seemingly from nothing. They don't come from nothing. They come from energy exciting the formless potential of the fields. And when a particle and its antiparticle meet, they annihilate. The two ripples meet, cancel each other out, and their energy is released back into a different field. The field itself remains, having calmed back down. The things were never the permanent reality. They were just temporary patterns of energy on a more fundamental substrate. Now, let us stand back and compare this to the ancient riddle we began with. Anaximander's asterisk appear an asterisk. A boundless and indefinite substance, from which all definite things arise and to which they return. Aristotle's prime matter asterisk. An ultimate substrate with no properties of its own, but with the pure potential to receive any and all forms. The quantum field. An invisible, omnipresent substrate that fills all of space. In its ground state it is formless, but when excited, it gives rise to the temporary, localized forms we call particles. The parallel is not just poetic, it is a quiet, structural resonance across millennia. The quantum field is the modern, mathematical description of what the Greek philosophers could only touch with abstract reason. What they called the formless, we call the quantum field. What they called the generation and corruption of forms, we call the creation and annihilation of particles. The ancient philosophers were dismissed for suggesting that reality's ultimate ingredient had no form. Yet here we are, at the edge of science, having peeled back the layers of reality, only to find their strange idea looking back at us. The ultimate ingredient is not a tiny, solid thing. It is a formless, invisible, vibrating potential that fills the universe. So, what does it mean to live in a universe where the fundamental ingredient has no form? The implications are not just for scientists. They gently shift our most basic intuitions about the world. First, it changes what we mean by solid and empty. We see the world as solid objects separated by empty space. But quantum field theory tells us this is an illusion. There is no such thing as empty space. A vacuum is not nothingness. It is the ground state of all the quantum fields, humming with a quiet energy. The emptiness of space is in fact a plenum, a fullness of potential. And the solidity of a chair? The feeling of solidity you experience when you touch it is not tiny, hard atoms hitting other hard atoms. It is an electromagnetic force. The electron field in the atoms of your hand is repelling the electron field in the atoms of the chair. You are feeling a force interaction between two localized patterns of vibration in an underlying ocean of potential. In this view, the universe is not a collection of separate objects. It is a single, vast, interconnected whole. There is just one electron field, for example, spanning the entire cosmos. Every electron in the universe, in your body, in the furthest star, is just a ripple in that one, single field. The electrons are not truly separate. They are all manifestations of the same underlying reality. This gently blurs our concept of individuality. If you and I are ultimately just fantastically complex patterns of vibration in the same set of universal quantum fields, what does that say about our separateness from each other, and from the cosmos? It suggests a universe that is far more holistic than our everyday experience implies. This modern scientific worldview also recasts the ancient relationship between being and becoming. We tend to think of reality as made of static things that then happen to change. But the QFT picture, much like the philosophy of ancient thinkers like Heraclitus who said, "Everything flows," suggests that becoming is more fundamental. The universe is not a collection of static things. It is a process. The fundamental reality is the dynamic, ever-fluctuating behavior of the fields. The things, the particles, the atoms, are temporary, semi-stable patterns that emerge from this constant flux. We are not nouns, we are verbs. We are not objects, we are processes. This perspective can be humbling. It means the solid, stable world we perceive is a low-energy illusion. Underneath it all is a reality that is indeterminate, probabilistic, and fundamentally formless. It means the stuff we are made of is, at its root, no stuff at all. It's pure potential. But this can also be a source of profound wonder. It paints a picture of a universe that is not a sterile machine, but a vibrant, creative process, constantly giving birth to form and structure out of a formless sea of potential. The laws of physics are the rules that choreograph this dance of energy, the rules that allow for the emergence of temporary, beautiful, complex forms like stars, planets, and people. We began with a seemingly abstract idea from 2,500 years ago, that the foundation of reality is a formless potential. We saw how this idea was quietly set aside by a new science that believed in a world of solid, definite things. And we followed the story of how that same science, by patiently pushing its own methods to their limits, found its way back full circle. It found a universe whose fundamental substrate is not a particle, but an invisible, formless, omnipresent field. A modern, mathematical echo of the ancient apeiron. The journey shows us that the history of thought is not always a straight line, but a quiet conversation across centuries. It tells us that our intuition, so useful for our everyday world, can be a poor guide to the fundamental nature of things. And it reveals a universe far stranger, more interconnected, and more mysterious than we might have imagined. The next time you look at your hand, or at the stars, or at the solid ground beneath you, remember what you are truly seeing. You are not seeing a collection of separate, solid things. You are seeing a shimmering, dynamic dance of energy. You are seeing temporary forms, ripples on the surface of a vast and formless sea of pure potential. The ultimate ingredient of reality is not a thing you can ever hold. It's the potential for everything. The edge of reality where language fails. There is a scale in our universe where the word thing loses its meaning. It is not a specific location, but a fundamental layer of reality, deep within everything we observe. At this scale, asking, "What is it?" may be the wrong question. To illustrate the problem, consider trying to describe the color blue to a person who has only ever perceived the world in grayscale. You could use analogies: the sky, the ocean. You might associate it with concepts like peace or sadness. However, the direct experience of the color would remain inaccessible. The words you use are an inadequate tool for conveying the reality. When we examine the smallest scales of the universe, we face a similar challenge. The part of reality we do not directly perceive operates by rules so different from our own that there are no direct analogies. In this video, we will explore that frontier. We will move past the limits of our everyday intuition and sensory experience to the fundamental edge of reality, where our language begins to fail, and we are faced with the underlying structure of the cosmos. The journey begins. Our journey starts not with a complex equation, but with an ordinary object. A ceramic coffee mug on a desk. It appears solid and real. It has a definite mass, shape, and location. Tapping it produces a distinct sound. This is the macroscopic world our language and intuition evolved to navigate, a world of objects. However, this perception of a solid, continuous object is an emergent property. The underlying reality is quite different. Let's begin our descent in scale. Zooming in, the smooth surface of the mug resolves into a landscape of crystalline structures, a tightly packed lattice of molecules. As we push further, the arrangements of these molecules, silicon, oxygen, aluminum, become visible. At this microscopic scale, a single bacterium would appear enormous. The familiar rules of objects and locations still seem to apply, for the most part. Let's continue. We can single out one of these molecules. You may recall the ball and stick models from chemistry, where atoms are represented as spheres connected by rods. This model is a useful abstraction that helps us understand how atoms combine to form substances. It provides a story of definite structure and arrangement. This story is incredibly useful, enabling fields from medicine to materials science. But as we go deeper, this abstraction, like all models, begins to break down. The balls and sticks are metaphors. And with increasing scale, our metaphors become less and less adequate. We are about to cross a threshold from the chemical world into the quantum realm, a place where the very concept of a thing is challenged. The solid mug is about to be redefined as a structure of probabilities. The atomic illusion. We will now focus on a single atom in the molecular lattice. The classical picture, often seen in older textbooks, is of a miniature solar system. A dense central nucleus with electrons orbiting it like planets. This image is orderly, intuitive, and fundamentally incorrect. The first indication of this came from the double-slit experiment. Imagine firing particles, like small projectiles, at a barrier with two slits. A detector screen behind the barrier would be expected to show two bands, corresponding to the paths through the slits. When this experiment is performed with electrons, the result is different. Instead of two bands, we observe an interference pattern, a series of many bands that is characteristic of waves interfering with one another. Yet, we can detect electrons as individual particles. To investigate this, let's slow the experiment down and fire one electron at a time. Each electron makes a single, discrete impact on the screen. It arrives as a particle. But over time, as thousands of individual impacts accumulate, they build up, dot by dot, to form that same wave interference pattern. This implies that each electron, traveling alone, interacts with both slits. It behaves as a wave of possibility during its journey, then collapses into a particle at a definite location upon measurement. This is wave-particle duality, a core principle of quantum mechanics. An electron does not behave exclusively as a particle or wave. Its description depends on how it is measured. It is something for which our classical vocabulary is insufficient. So, what are electrons doing inside an atom? The Schrödinger equation, a central equation of quantum mechanics, provides the answer. When solved for an atom, it does not yield a defined orbit. It provides a wave function which describes a cloud of probability. This function tells you where an electron is likely to be found if a measurement is made. For a hydrogen atom in its ground state, this probability distribution is a fuzzy sphere around the nucleus. The electron is not in orbit, it exists as this spherical distribution of potential locations. These probability clouds are called orbitals. They are not arbitrary, they are constrained to specific shapes and sizes, corresponding to discrete, or quantized, energy levels. An electron can exist in one of these specific energy states, much like a guitar string can only vibrate at specific resonant frequencies. It can transition between levels by absorbing or emitting a precise amount of energy, but it cannot exist in a state between these quantized levels. Adding to this is the Heisenberg uncertainty principle. It states a fundamental limit on what can be known about a quantum system. One cannot simultaneously measure both the exact position and the exact momentum of a particle like an electron. The more precisely one property is measured, the less precisely the other can be known. This is not a limitation of our measurement tools, it is an intrinsic property of nature. If an electron had a perfectly defined location, its momentum would be completely uncertain, and vice versa. Revisiting our atom, we see it is not a miniature solar system. It is a nucleus surrounded by a haze of probability, governed by strict rules of energy and uncertainty. The electrons are not in a specific place. They exist as fields of potential that resolve into a particle at a location only upon interaction. The atom is best described not as a physical object, but as a system defined by probabilities. The apparent solidity of our mug is becoming less straightforward. The historical interlude. This departure from classical intuition was the source of one of the most significant scientific debates of the 20th century. The discussion centered on the nature of reality itself, and featured two of the era's leading physicists, Niels Bohr and Albert Einstein. In the 1920s, a group of physicists led by Niels Bohr developed the Copenhagen interpretation. This is the view we have been exploring. At the quantum level, reality is fundamentally probabilistic. The wave function is a complete description of the system, not a placeholder for some hidden, more detailed reality. A particle does not have a definite position before measurement. The act of measurement forces a probabilistic outcome. Einstein found this interpretation philosophically unsatisfying. His statement, "God does not play dice," was an expression of his belief in an objective, deterministic universe. He was a realist who maintained that physical objects have definite properties, regardless of whether they are being observed. He argued that quantum mechanics must be an incomplete theory. There should be, he proposed, hidden variables, local, underlying properties not yet accounted for, that would restore determinism and predictability. The Bohr-Einstein debates consisted of a series of thought experiments proposed by Einstein to find inconsistencies in the Copenhagen interpretation, which Bohr and his colleagues consistently resolved. For example, Einstein would devise a scenario that appeared to violate the uncertainty principle, and Bohr would demonstrate how the framework of quantum mechanics, sometimes using Einstein's own theory of general relativity, accounted for the outcome. At its core, their disagreement was about the relationship between language and reality. Bohr argued that classical concepts like position and momentum do not apply to the quantum realm in the same way they do in our macroscopic world. Forcing these everyday terms onto an electron is a category error, like asking about the color of a sound. For Bohr, the reality was precisely what the theory described: a world of probabilities and quantum states. For decades, this remained a largely philosophical argument. Then, in the 1960s, physicist John Bell formulated a theorem. Bell's theorem showed that if Einstein's local hidden variables were real, the statistical results of certain experiments involving entangled particles would be constrained below a specific limit. If quantum mechanics was correct, however, that limit could be violated. When these experiments were performed, the results were unambiguous. The experiments consistently violated Bell's inequality, lending strong support to the predictions of quantum mechanics over local hidden variable theories. The universe, at its fundamental level, does not appear to operate according to our common sense rules. This history shows that the founders of the field were themselves the first to confront the gap between physical reality and our ability to describe it. The molecular deception and the nuclear fire. With this quantum framework in mind, let's return to our journey of scale. We were examining the ball and stick model of the mug's ceramic structure. We can now see that this model is not just an abstraction, but one that obscures a more fundamental reality. The sticks, representing chemical bonds, are not physical connectors, but regions of overlapping electron probability clouds. A deeper issue lies with the balls representing atoms. Quantum mechanics includes the principle of indistinguishability. Two identical particles, such as two electrons, are fundamentally indistinguishable. There is no electron 1 foot and electron 2. There is only the electron field. This has direct consequences for our concept of structure. Consider the H3+ ion, composed of 3 protons and 2 electrons. The 3 protons are identical and cannot be individually labeled by the universe. The complete quantum description of this system is a superposition of all possible geometric configurations. The structure we observe is a statistical average that emerges from this quantum superposition. The idea of a definite molecular skeleton dissolves into a distribution of probabilities. It's at this point, where our familiar concepts become insufficient, that we recognize how much remains to be understood. If you find this exploration of fundamental questions interesting, consider subscribing and enabling notifications. This channel is dedicated to these topics, and your support makes these deep dives possible. Now, let's continue our descent. The nuclear fire. Let's move past the electron orbitals and into the atomic nucleus. For a time, protons and neutrons were considered fundamental particles. We now know they are composite, each a complex system in its own right. A proton is composed of 3 smaller particles called quarks. 2 up quarks and 1 down quark. A neutron contains 1 up and 2 down quarks. These particles have fractional electric charges, plus 2/3 for an up quark and minus 1/3 for a down quark. These fractions always combine to form the integer charges of composite particles like protons and neutrons. The force holding quarks together is the strong nuclear force, mediated by particles called gluons. Quarks and gluons possess a property that physicists have labeled color charge, which comes in 3 types: red, green, and blue, and their corresponding anticolors. This is simply a naming convention for a physical property with no analog in our macroscopic world. A stable composite particle must be color neutral. A proton, with a red, green, and blue quark, is color neutral. The interior of a proton is a dynamic and complex system of quarks and gluons constantly interacting and exchanging color charge. This force gives rise to a property called confinement. An individual quark can never be isolated. If you attempt to pull 2 quarks apart, the energy in the gluon field between them increases until it is sufficient to create a new quark-antiquark pair. Quarks are permanently confined within larger particles. There is another force at play here, the weak nuclear force. At these subatomic distances, it is weaker than the strong force in electromagnetism, and it has a unique function. It can change a quark's flavor or type. For instance, a down quark can become an up quark. This process is responsible for some forms of radioactivity, such as when a neutron decays into a proton. The weak force also exhibits a strange asymmetry. It only interacts with left-handed particles, a quantum property related to a particle's spin and direction of motion. It effectively ignores right-handed particles. The reason for this is one of the unsolved problems in physics. The nucleus, then, is not a simple collection of parts, but a maelstrom of forces, transformations, and symmetries. The edge of reality. We have examined the layers of the mug, from molecules to atoms to the quarks and gluons within the nucleus. What happens if we try to go further? Here, we move from established physics into more speculative territory. Modern quantum field theory, QFT, proposes that the most fundamental components of the universe are not particles, but fields. There is an electron field that permeates all of spacetime. What we call an electron is a localized excitation or vibration in this field. There is an up quark field, a gluon field, and so on for every fundamental particle. In this view, reality is a set of interacting fields, and particles are the manifestations of their activity. The field view also helps to contextualize one of quantum mechanics' most confounding phenomena, entanglement. Imagine two particles are created such that their properties are linked. For example, their spins must be opposite. Until a measurement is made, neither particle has a definite spin. They exist in a superposition of states. If you separate them by a vast distance and then measure the spin of one particle, you instantaneously know the spin of the other. The outcome of the first measurement is correlated with the outcome of the second, faster than any signal could travel between them. Einstein referred to this as spooky action at a distance. Experiments have repeatedly confirmed that this correlation occurs. Entanglement challenges our concept of separation. The two particles are best described as a single, unified quantum system, regardless of the distance between them. This suggests a form of structure based not on location, but on a non-local connection. This brings us to the theoretical limit of our current physics, the Planck scale. The Planck length, approximately 1.6 by 10 cubed to the power of 5 meters, is a scale so small it is difficult to create an analogy for. But to offer a sense of it, if you were to scale a single atom to the size of the known universe, the Planck length would be about the height of a tree. At this scale, the equations of both general relativity and the standard model of particle physics break down. To describe this realm, a theory of quantum gravity is needed. We do not yet have such a theory, but speculative frameworks like string theory and loop quantum gravity offer potential glimpses. They suggest that at the Planck scale, spacetime itself may no longer be smooth and continuous, but a fluctuating, quantum foam. The concepts of location and moment may cease to be meaningful. This is the ultimate failure of our language, because it is built upon the grammar of space and time. Here, at the most fundamental level we can currently conceive, we may not find things in any conventional sense. We may find pure information, networks of relationships, or something for which we have no concept at all. Conclusion: our journey began with a solid coffee mug and ended at the Planck scale, where space and time may dissolve into a probabilistic foam. At each step, our intuitive, macroscopic world gave way to a description based on probability, fields, and non-local connections. We saw the classical atom resolve into a cloud of probability. We saw chemical bonds redefined as overlapping electron wave functions. We examined the nucleus and found a dynamic system of quarks and gluons governed by complex forces. We then arrived at the speculative edge of physics, where spacetime itself may break down. At every stage, the physical world appeared less like a machine made of distinct parts and more like a complex, interconnected system. Our language, developed for a world of medium-sized objects, is not well suited to describe this underlying reality. As the physicist Werner Heisenberg noted, we cannot speak about the atoms in ordinary language. We are attempting to map a new territory with an old alphabet. So we return to the initial problem: describing a reality for which our words are inadequate. The mathematics of quantum physics provides a language that can predict the behavior of this world with incredible accuracy. But it does not offer an intuitive, one-to-one translation into concepts our minds can easily grasp. This leaves us with a necessary sense of intellectual humility. The fundamental nature of our physical reality is not something we can easily picture or describe in everyday terms. We can observe and predict its behavior using the precise language of mathematics, but a direct, intuitive translation into our everyday experience remains elusive. The effort to better understand it, to find new models and new ideas for this ultimate frontier, continues.